Morning. I think it's time to start. So the first speaker of today is Professor Esther Cabezas Rivas. She will speak about geometric analysis meets image denoising. Thank you.
So first of all, I would like to thank Alessandra and Andrea for the nice invitation. It's always a pleasure to be back in Pisa. And this will turn out to be a Blackboard talk in a minute, but as you may imagine, I have to show images at some point. So, and because of the layout of the lecture room, I really need to stick all them at the very beginning, and then I will start doing things on the Blackboard. Everything I will tell is joint work with two colleagues from Valencia, Salvador Moy and Vicent Pallardó. And the idea is to see how geometric analysis may have a say in different areas, right? Like in this case, image denoising. So let me put you first into context. Imagine that I give you some grayscale image that can come from, I don't know, a photograph of this. No, I don't. Oh, you don't have I explicitly. So I raise my voice. So imagine that comes from the one of these fancy telescopes that are like trying to catch black holes, you know, that have been a redundant topic in this conference, or a magnetic resonance of your brain, right? And mathematically, very roughly at the very beginning, you may model this as a function on a bounded domain, the plane, imagine your computer screen, and taking real values in a grayscale. And then the goal is to improve the quality of the image by reducing some noise. And the idea is that this will resemble somehow the denoised image after this filtering. It resembles some kind of an ideal clean image that you obviously don't have direct access to, right? So, and where analysis comes in, the analytical question in this setting is whether regularity survives to this process, meaning that if you assume that your source is in your favorite regularity space, I don't know, ellipsis, continuous, whatever, if this is inherited by the output. And the best known result till the date, or that we know, is from Casellas, Chambol, and Novaga. Mateo is not here, so I can't say anything. But so what they do, the thing is that they assume that you have a C01 function, and they also assume some extra condition that your domain is convex, and then you prove that the output keeps so. Therefore, somehow that was the best known result in 2011, and it lasted for like 10 years, like so, because it was still Alessio Porretta in 2021 that he was able to remove some kind of this extra hypothesis that you don't want to have there. And as I really like to state a theorem in the first 5 minutes of the talk, so that you can then reset if you wish and know what I did. Even if this is still meaningless, unless I tell you which precise model I use for denoising, that will come. But even in this abstract sense, we generalize the classical results in 3 different directions. First, we consider the vectorial version, which is not so amazing, but it's also non-trivial, because somehow the regularity theory up to the boundary doesn't follow from classical results. But as this is not thrilling, just put some rock and roll to the game and consider it manifold constraint. Meaning that I consider that F lies in some n-dimensional complete manifold, almost everywhere. And if you wish for some of the arguments, we need to consider this manifold as isometrically embedded by Nash in some higher dimensional Euclidean space. And well, why not? Nowadays, your computer screen doesn't need to be flat anymore, right? So the last twist will be to consider a curved domain that will be your omega is a compact surface with non-empty smooth boundary. We also have the corresponding result for signal denoising, meaning that this is one-dimensional, and we have some kind of stronger result. I will tell in a little bit. But with this, in this generalizing the problem in these three different directions, we are able to prove exactly the same result without any need of convexity assumption, and that's what we do in some preprint at the last, which is on the archive in December of last year. So, as I said, this is meaningless unless I explain you more about what's the model. That will come in a minute. But also, it's nonsense for image processing, because somehow your function or your image, unless it is a dark spot, only a dark spot, won't be even continuous. You will have jumps in your image. So the interesting thing is to have the localized version of this result, and we and also all the previous ones have it. So that's the result. I will give you the details of the proof once I tell you how to model this and why, and especially I have to convince you why manifold constraint version of this problem is important. But let me give you more details about how to model this denoising. Well, imagine we have like some picture of a blackboard, and let's put it in a grayscale. And now I consider it as a graph. This photo, I consider it as a graph by setting it in a grayscale from taking 0 value is black and 1 is 1. And then you have all. But now we should add some noise to this image. So if you add some noise there, then you will have here corresponding like gray pixels flying around. Let me denoise the image with some denoising algorithm. And you may think, well, what's that? It's so messy as the previous one. But if you smash it down and project it over, your image has already improved. So, and well, you see here that there is kind of in this corner, like a white spot. You may not, well, you may think it's a default of the image, but actually it's a bit of this during a lecture. So, well, now that I have all the Italian audience in my pocket, I can continue. So, in order to say you how this denoising or which model I use for that, I need to understand how the noisy image is constructed from the original one, from the ideal one. Well, what a question, adding some noise. But wait, on my innocent sentence, adding some noise, I'm already assuming an additive ansatz instead of a multiplicative one, for instance. And also then you have to decide how you alter its pixel with random variable or with which probability model you do. The typical and the most common example will be to consider, like here, independently, identically distributed zero mean Gaussian measures. And then the goal, well, notice that I am using the same letter for the denoise and for the original. Well, the goal is to maximize the probability of, if I know the noisy image, to recover the original one. We all know from basic probability lectures Bayes' theorem. So if this probability of F knowing U times probability of U divided probability of F, but for the maximization problem, it doesn't matter. And well, what's up here? If I know U, the probability of knowing F is the probability of knowing the noise. And that's something that is in my assumption. So that will be this exponential, negative exponential. So the nature of this problem is asking me to take negative logarithms and then convert this into a minimization problem. Right? So I will write it on the board once I can access the board. So the only thing that I want you to keep in mind is that when I take the negative logarithms, I will have the sum of two terms. This kind of integral of the difference between source and ideal one, and an extra term which this is kind of a fidelity term. This penalizes being too far away of the original image. But then I have to smooth out my original image. In geometric analysis, when we talk about something that has smoothing power, the first thing that comes to our minds is the heat equation or some Dirichlet energy, right? But if you do some denoising based on the heat equation, you will get something like that. So a blur image, and that's not what you want to have. So somehow you need to have a milder filter to regularize in order that you keep the discontinuities across lines so that borders or edges of objects are preserved after denoising. So we will see how we do that. But before doing that, let me try to convince you why working on manifolds is not like by the sake of, so my co-authors are analysts, so it's not by the sake that I want to upset them, like bringing them to a curvature wall. It's like a demand of actual applied literature. So there are, well, the easiest example to grasp is the tracking of motion that you need for animation or video surveillance, where your data, as they are moving, it takes values in the space of rigid motions of Euclidean free space. Another example that we all know is the RGB color scheme that we always with LaTeX. Sometimes we choose the right value for red, green, and blue. So the images take vectorial values, right? And if we have a noisy image, that will be such a function. The algorithms don't work directly with the vectorial function. They split it into data. First, the chromaticity, that's the actual color. And then at each pixel, you put like a brightness or an intensity. This is a scalar value, so you apply the scalar algorithm. I will tell you what rho is. It's the name of the algorithm. And but this, and if you denoise it, you will have something like that. But if you, yeah,
you have the brightness.
That's what what's it called? I think if I don't. Well, whatever. And then, okay, so, and the point is that you have whatever you call that, okay? This takes values on an S2, so you need a manifold valued denoising algorithm. And when you join both of these data, you get your denoising. So that's the easiest example where you need manifolds, but there are fancier ones, which I like. So I tell you, don't ask much about them. So there are like in biomedical imaging, there are like these so-called diffusion tensor magnetic resonance images that take values in a non-positively curved manifold, where in each point of your brain is represented by an ellipsoid, which is like a 3 times 3 symmetric positive definite matrix. And my favorite example is like people nowadays, seems crazy, but they are doing that and they claim that it works super well. They are doing machine learning and image segmentation using hyperbolic space. So you have a photograph, you have the hyperbolic disk, and you divide it into regions with several colors to recognize, I don't know, blue is the sky, green will be the sea, the people will be yellow. But when you are training your model, there are some errors. So you have some noise there. So that will be this black pixel. And then it may happen that, you know, the kite is like the sea. So if you previously to this process, you will, the noise, this, you will may have better pattern recognition. And somehow the idea or how they justify this is because in machine learning, like the growth of information, the nodes grow like hierarchies, which grow like exponentially, which mimics the volume growth of hyperbolic space rather than the polynomial one of the Euclidean one. And that's why somehow this works better. Okay, so let me remember that maximization problem that we have. And the goal is equivalent to minimize in U. And we will have some kind of a first term that will be the smoother. And then you will have the fidelity term. The fidelity term, well, the 1 over sigma squared, let me put it some lambda. Lambda over 2 was the integral of the noise. That was f minus u squared. I'm going to do it first in the Euclidean space and then modify whatever for manifold. And so if I already write the Euler-Lagrange equations for this, I will have from the fidelity term, this is kind of a weight that you can get better or worse results by somehow balancing how strength is the fidelity versus the smoothing power. So here you will have minus lambda f minus u. That will be your equation almost everywhere in omega. And here, well, you have several choices, right? You will, first thing that you will try is the Dirichlet energy, but that will put here the Laplacian. And as I said, you will get this blur image. So that's not a good idea. The milder regularization that you will have is what is called total variation functional, where you remove this square. That's the rough model from Rudin Osen-Fatemi from the 92, and but you pay the price of this degeneracy. The good thing about this is that if you minimize in the right space, that will be functions of bounded variation. It is expected that discontinuities are preserved, and somehow that what is known as, that's proved by Caselles, Tambol, and Novaga, is that no new discontinuities appear. That is, you won't have more jumps than A, for example. And okay, so that's the equation. That's a boundary value problem. So what you will have is that if I have here, whatever comes there, I call it set. And in the normal direction, there is no flow out of the boundary, meaning that which makes sense. There is no flux through the boundary, so which makes sense for image processing. That will be almost everywhere on the boundary. And so that's your PDE there. Let me tell you that from the point of view of geometry, that's especially interesting also, well, from the PDE point of view, you may study existence, uniqueness, regularity, all this stuff coming from a variational problem. I didn't close this here. And But also you can, well, let me call this problem P to refer to it later on. But if I consider the sub-level sets of this, so ET, so the solution bigger than T, that can be interpreted as a prescribed curvature equation, mean curvature equation. So the mean curvature of the level set equal minus lambda F minus B. And actually, that's not by chance. First, that is not surprising, because if in the total variation, if I stick instead of U the characteristic of some subset of omega, I get the perimeter of that subset within omega. And so minimizing perimeter, you will get mean curvature. And the second thing, exactly the proof by these guys goes by studying the regularity in terms of the distance of any of the level sets of the solution. So more things to say about this. Well, let's go to manifolds already. So I'm going to consider the problem on manifolds, meaning that I will consider omega t, and that goes into N8. In order not to mess a lot with the notation, let me keep gradient U as alias for du, the typical one form that you knew from harmonic maps, right? So that will be in a section of T omega cos T star N. Then what you will have is first integrate with respect of the volume element. Then you will have the divergence of the domain metric. And here it does not make any sense anymore, because these are points on your manifold. So you will consider the geodesic distance, these two, to the square. And obviously that's also have no sense. So if I have U and F there, I have to put all this to a vector like here, that will be through the inverse of the exponential map. So here you will have X U, because that's in that point, right? X U minus 1. Okay. So that's the problem on manifolds. And then I think that's it. Let me try to give you a hint of how the proof works. So first thing we are going to study is existence and uniqueness. As you may have in mind from theory for harmonic maps, because if lambda is equal to 0, our results can be seen as a generalization of the classical theory, regularity theory for harmonic maps in the sense of Ilse, Samson, Sachs, Uhlenberg, and so on. So I will need some hypotheses on the target, right? Because you know there are some examples by Riviere that prevent that you get full regularity unless you put here some topological or geometrical restrictions. But they will pop up in the proof naturally. So I'm not going to make you the spoiler yet. So in order to be able to apply the direct methods of calculus of variation, I really need to gain some coercivity in my functional. So I really need to have here some further parameter sigma over 2 and some Dirichlet energy. So that will be 2. So smoothing power, fidelity, and here you gain coercivity and ellipticity. Obviously, I will let, so the thing is to let sigma go to 0 later on, but that will modify here, will have plus sigma gradient U. And that's of independent interest because in that way, this is kind of a perturb, so that you will have sigma times the rough Laplacian, or if you are more used to that notation, that's the tension, right? That's both typical notations, and plus the one Laplacian, so the corresponding one tension. So the point is that this is known as perturb one Laplacian equation, and which was the regularity of this problem has been studied by here and collaborators very recently, and also it has interest from fluid mechanics, because if you I put here and it's an equal missing somewhere. Sorry. So if you understand this right-hand side as, which is a vector field, as the gradient of some function or the gradient of some pressure, this equation models the steady behavior of a typical non-Newtonian fluid where sigma controls the viscosity and this controls the plasticity. So somehow, what I want to, in the marketing part of the talk, what I want to sell you is that this is a variational problem that has interest from the PDE analytical pure point of view. Applications to image processing can be understood from a geometric point of view. Also, Jürgen just studied the problem itself without this for like a shifted spectral problem on Riemannian manifolds. Also interested in fluid mechanics and generalization of, if lambda is equal to 0, generalization of the typical regularity of P harmonic maps in the unfriendly situation that P goes to 1. Okay, so uniqueness. I'm going to start with the uniqueness of the problem. For the uniqueness, it is very convenient that you have strictly convex functional. But, well, what's out? First difficulty is that you only have that for, not even look at the other two. For the distance square in a manifold, that only happens within the convexity radius somehow. So you have to add some kind of small range hypothesis in order to overcome this. You will need to add as an extra hypothesis that f of omega lies within some geodesic ball, center of E, radius r, with r smaller than the upper bound for the convexity radius, which is the typical 1/2 minimum of the injectivity radius. And in case you have positive curvature, that will be P pi over square root of an upper bound for the sectional curvatures. And if you are in that range, let me tell this ball B. You should prove, and it's not difficult to do that, we prove that this keeps for the solution after denoising, so U of omega also lies in B. Therefore, where we prove existence happens in the class of admissible minimizers that you will need to have W12, so that this is integrable. So will be in W12 omega n, and with this small range condition. So somehow, if you are in this set, we prove that the functional is the typical things: coercive, low, bounded below, and lower semi-continuous in the space of bounded variation functions in intersection with L infinity. But that's kind of routine thing. What is really hard and really surprising that nobody knew or wonder about that is, well, what about the total variation? So is the total variation as strictly convex? Well, along geodesics. And the answer is no way. So it is not, because there are examples for positive curvature. Therefore, you are forced to add not only this, but also that n is non-positively curved. Which is, well, let me take it here, complete non-positively curved. Well, the small range, you keep that in mind. So, which are also the unsurprising hypothesis if you are familiar with the theory of regularity of harmonic maps. Somehow, well, the difference is that these classical works of Il Samson and Sachs Uhlenbeck work in the nicer situation that you have Dirichlet boundary conditions. So our work is more similar in that sense in spirit to Hamilton's work previous to the invention of Ricci flow, about harmonic map, Newman problem for harmonic maps. The only thing is that we don't have harmonicity, right? So in all the computations, we will have some tension terms which don't vanish. And in all the previous literature, these terms are harmless because they are zero, right? So I'm saying that because obviously I'm not going to give you the details, but because I don't have the time. But the point is that for the non-positively curved space, you from scratch, because we thought, no, somebody has computed that. No way. We look for days, weeks, and then you have to like work it yourself from scratch. And so from the second variation formula, you get the geodesically convexity in C infinity beyond omega, which will be great if this is dense in the space you need, yeah, which is not the case. But luckily, in our not in general. Let me just say in words what we do. In our case, as we are within a geodesic ball, we can apply a trick that we learned from Pigola Veronelli. That is kind of patterning out the ends on your manifold outside the geodesic ball, in order that you can kind of construct a global system of normal coordinates from this pole in such a way that you don't destroy the strict convexity of the distance. And in that particular situation, you prove the density. And also, we push these results further, and we do it for more general energy functionals in order to have a proof that was not available in the literature for the geodesic convexity of the total variation functional in the class of BB functions, which is not, it was not even defined on manifolds, so we give a proper definition of that. But well, as it doesn't enter into this proof, let me keep it for a moment. Okay, somebody told me that. So now the important thing is regularity, because existence and uniqueness, well, it's much or less harder, but you hope to have that. But how you prove regularity? So the point is that, and well, I wanted to first make some remarks. We have ellipses, and people coming from differential geometry or a smooth ball may think that ellipsis is too few, but in this set two, I made it the other way around. Okay, wow, that's right. Yeah. If not, no, let it I read this before. Okay. So the point is that if you even have a function which is C infinity with compact support, you may reduce the total variation by truncating it appropriately. And therefore, the best you can hope for a minimizer is that to be ellipses. And also, that's a drawback of this rough model that you in further works try to improve, that it tends to create stargazing phenomena, like zigzagging in the boundaries of your images. So that's an issue. Let me go back. Sorry. Well, and I said, because otherwise I forgot, that that's a hypothesis, but for the Mosolov problem, meaning that for sigma positive, for sigma strictly positive, we get the regularity result without any curvature assumption. Also for the positively curved. But well, the proof is hard and long, and we didn't push it to the limit of sigma going to 0. So, okay, now after the accident with this, let me continue. So, the regularity, I like the proof because it shows very well the interplay between geometry and analysis, because the first part I'm going to tell you only works if you are good intrinsically. Extrinsically, well, my colleagues are analysts, so the first thing you give them a manifold and say NAS in Rn, and I will live safe in flatland, right? But here it doesn't work, that strategy. But the second part I will tell you is the other way around. You need PD theory, adapting classical things from PD theory, which are only available in Euclidean space. So you really need to work extrinsically. So without the interplay of geometry and analysis is not possible. So the point is that, well, again, so first thing you need is to remove the degeneracy of this equation, sticking the typical epsilon. So here you will have square plus epsilon squared, and meaning that here you will keep the plus epsilon squared. So you regularize this problem in this way. Notice that we have 3 parameters already that we will let go to 0, well, 2, epsilon and sigma. And another thing is that I'm going to go to use before raising and lowering it. I say it before this time, I plan it. So the point is that you need to differentiate. The Bernstein technique is differentiating the equation and multiply it by du. The projection on the tangent, no. Here I'm making it intrinsically. You can also project on the tangent if you use the, but that's already on the. Okay, so the point is that let's count 1, 2 derivatives. If I take another derivative, it's 3 derivatives. I'm trying to prove ellipses of U, and for proving that I need C3. Well, in classical settings, if you are in R, this trick works because people say that for the regularized problem with the epsilon, standard PD theory says that the solution is smooth. Let's believe it. I tell you, spoiler, it's not true in our case, but I will tell you afterwards how do we deal with that. So again, as I said, this is Bernstein technique. That we take derivatives in the problem. And as I said, you will need C3 up to the boundary, which is even worse. And but as I said, well, you may, if somebody's thinking, well, if you already have C3, you don't need to prove Lipschitz. I mean C3 without any control on the bounds, so that when you take epsilon and sigma to 0. So here I'm going to prove uniform Lipschitz estimate. So the point is that I define omega du squared and use the Berns-Bochner technique plus some comparison results for Jacobi fields to show that this omega satisfies an elliptic inequality. So that will be like L omega, where L is an elliptic operator, plus will be lambda omega. I'm going to be very sloppy on this at this point, so up to constants, you will have some terms that depend on the gradient and some lambda ETF squared. I'm not well. First thing is that your F was assumed only to be Lipschitz, so therefore what you need first is to modify it using some trick of Carher. So I will have here. And in such a way that the Lipschitz constant is not altered uniformly. So, so you have both control in both directions. Then you will have here some kappa omega squared, which somehow I write this so that you understand that what makes your life easier, where the non-positively curved target enters is here, because otherwise you have a quadratic term and you will get into troubles because it has the wrong sign. And then let me do some kind of baby case. So if omega is convex, it's not what you want, but you use the boundary condition. In case that omega is convex, in that case, you may prove that the normal derivative of omega is non-positive, which allows you to apply Hopf's maximum principle to say that the maximum of omega is not attained at the boundary, meaning that then you can assume that you are at a maximum interior point. At a maximum interior point, this thing, you can forget about that because this is bigger or equal than 0. This is 0. And then you have actually the estimate you wish. The du squared is smaller or equal than the Lipschitz constant of your data. But obviously, that's not what you want, because I said that we also remove this convexity condition, meaning that what you want is to remove this. What you, instead of this, define some kind of omega twiddle that will be T times omega, whether this is bigger than 1 unbounded, cutoff type function. And then you have to modify things a little bit, omega tildes all over the place. Here it comes some P. And here some terms which depend on first and second derivatives of sigma, which if you have like an appropriate good control of the growth, then you will get here terms of the on sigma omega twiddle plus square root of omega twiddle up to constant. But then you are in good shape because sigma is going to go to 0, so it's not a problem to take it smaller than lambda over 2, so that it's eaten by this term. And somehow, if you divide everything by the square root of omega twiddle, which is bigger than omega, you get exactly what you wanted to. That is like d omega smaller or equal, no, du, sorry, smaller or equal than some uniform constant, so that you can pass to the limit 1 plus d, or the ellipsis constant to the square. And the point is that this is uniform. And then also in sigma, delta, that is the Karcher parameter, and epsilon. And then can let this to 0 in different states is to have regularity for solutions of the Mosolov problem, which is of independent interest, and for the rough model.
Yes.
Yeah.
If the target is a manifold, do you have any assumption on the geometry of the manifold? Like
non-positively curved, and that
non-positive.
yeah. For sigma positive, nothing, only the small range. And okay, so and that's because of this. So if you want the local problem goes the same way, but so for the local version, so you only need that this is kind of supported in a small ball, and you repeat the process. And for the Mosolov problem, then the function has to depend also on the target, and that's much long and harder proof. But still, that in your better dreams, in that Alice in Wonderland that was in the Natus book, because that's not true, right? And and let me try to let you know what are the difficulties, because I won't have much time to say how we solve them. But first thing is that if you take, so we want to prove at least Felder regularity, and then bootstrap, and you don't, the constants, if they are not uniform, doesn't matter. And the point is that if you work in coordinates that are isothermal for omega and extrinsic, meaning you apply Nash here on n, then you can write your problem. I'm going to be very sloppy again. Will be like the divergence, that the Euclidean one, of some operator, plus here the second fundamental form of the target comes in, gradient UP, equal to something that has to do with the exponential -1 multiplied by the conformal factor, the isothermal factor. Right. The point is that this term has this kind of growth. That is what people working in this business call natural growth, nonlinear system, which is critical case for regularity. Somehow works by Giaquinta Modica and Hildebrand. So the classical thing is that interior regularity is fine only if sigma that controls your ellipticity is bigger than 2 this growth times the size of your domain, also of your domain in the target. But watch out, we want to make this go to 0. So that's no way. First thing, and second thing, we want, it's not enough for us to get interior regularity 1 up to the boundary. And how how we sort this up, let me, to get this work, let me do it. I don't get this. So I'm going to tell you only the key ingredient because we had to develop some theory in a separate paper, so that's auto-propaganda, so I should tell that. So the way out of this to get this P3, that in all the papers we know is one line, standard theory, right? So first thing we somehow, if you have your domain omega, we flatten out the boundary locally by covering it by isothermal coordinates. Oh, isothermal. So that will be the first step. And then we will work some kind of freeze a point there and consider small balls. And that will be what we call omega r. This is a ball of radius r. Then the point is that we need to be able to use something of the PD theory to adapt it to our setting. So we need that our equations live in Rn. So we need to extend the system over there to a tubular neighborhood of our geodesic ball to extend P suitably. I don't have time to give details to a tubular neighborhood of the ball, and then you will get sort of the philosophy is that you get some term Bx, divergence of Bx gradient u, and then you will have a tangential part plus a normal part. Splitting it in the when you project to the tangent space. So the philosophy here, so let me remark two things. That is because it is non-flat. So which makes all the estimates much more intricate. And second thing, that the natural growth comes from the second fundamental form, so all goes here. And we have a separate paper in nonlinear analysis published last year, in which the philosophy says that this smallness condition of the Giaquinta modica only applies to the tangential part. The normal part can be as huge as you wish. And in that paper, what we prove is, which is kind of of independent interest, is an intrinsic Cacciopoli inequality. Which is from us. We didn't know of any previous intrinsic version of this inequality in the literature. It's kind of the gradient on omega r of, so the integral of the gradient is control c over r squared integral of omega 2r by 1 plus distance squared to the barycenter. This will be the barycenter of this thing. And thanks to, which is classical, is that if you have a Cacciopoli inequality, you get higher integrability estimates. That's also of our work. You will get that your solution is W1Q of omega n. For Q, remember that we have existence in omega in W1, 2. We have bigger than 2. And then we push it to prove Helder regularities for the gradient. So then next step will be to prove that gradient U, or that U is in C1 beta for some beta. That step is also non-trivial. We have to adapt to our settings some very inaccessible papers of Arkhipova. Very inaccessible mean only in Russian, right? So we had fun to read them and then adapt to our setting. And then also continuity method in a subtle way to make bootstrapping work. and then we get the C3 that in all the other papers was 1 line. So let me finish giving you some open challenges. So that's what we wanted to do, but obviously we are not happy with some things. First thing that you want to relax is for the rough problem, this one. We believe that at least for the round sphere should be possible by what happens in harmonic maps, and also because they applied, like the RTB example, most of the applied examples go to the round sphere. So that's one of the interests. So first challenge will be allow sectional positive. Second one, well, why ellipses? The right setting will be bounded variation functions that have jumps. So what can you say if you have rougher initial data? Other thing is L1 fidelity term. Why is this interesting? First, it is more challenging because the function is not anymore strictly convex, and also it's known that new discontinuities can be created. But that's the drawback. But the advantages is that there are no star-casing phenomena with this model. That model is called from Chan SW. And also from the geometric point of view, it's contrast invariant or invariant under homotopies. So it's geometrically more meaningful because the images won't change under contrast. And well, that's dreaming with a high voice, but why not? Instead of manifold constraint, I can consider a cat0 target space if I still want to live in a non-positively curved world, and with an RCB domain. That's not a naive dream, because for the harmonic map theory, the ellipse irregularity in this setting was established by Nicola Gigli about 2 years ago. And also, we would like to study regularity in this intrinsic way, like throwing all the smallness condition to the normal part for more general operators, depending here, for instance, of U also with some conditions to have electricity and so on, to include P Laplace operators and so on, in order that, as this has been useful in our setting, if we study more general problems, we will hope to gain some insight. And well, as I said, if this is a fairy tale, the moral will be that Bernstein technique, as here, can only work with intrinsic geometric methods, working intrinsically in your manifold, but all the PDE theory to establish that this is possible to be made has to be made extrinsic with analytical methods, and that's this interplay of geometry and analysis, and that's where geometric analysts have a say, even in this image processing world. So thanks.
For the nice talk. Are there questions or comments?
Yeah. Thank you for the beautiful talk. I think I didn't understand one thing. In the Bochner computation there, okay, in the maximum principal argument, the curvature of G is in some constant there? Or...
Appears somewhere the Ricci curvature, but you just, as it is compact, it's not extra assumption to assume that this is bigger or equal than some constant times.
Okay, but it appears. Oh, okay. Thank you.
Thank you. Other comments?
Yeah, I was wondering in the case of, say, compact targets, so whether you can still prove minimality, and maybe because the cut locus have a small measure, maybe one could hope for a partial regularity.
That's the most. We haven't looked at that. Sure.
Okay, thanks.
So there are some results for minimizer or double phase functional in the spherical target, where somehow the projection you can make it. I mean, you can just write it vector over the normal vector. So maybe there is how.
So somehow the parabolic version of this is much easier. So for us that come from flows and so on, it's like we have the elliptic regularity there, minimal surfaces and all that, and that's kind of the first thing you have as a black box, and then you do the parabolic. Here is the other way around. In the parabolic case, there are results of Michael Alford and so on with, as you said, you work extrinsically, you know exactly the second fundamental form, how it works, and you do that. In that case, we tried it and it didn't work. With these techniques, I tried everything. So one needs some, and that thing of the projection I also tried.
Thank you. Comments or questions? So if not, we thank again the speaker. So the last talk of this morning is by Deborah Impera from Polytechnic di Torino. The title is Isoperimetric Inequalities on Manifolds with Asymptotically Non-Negative Curvature.
Okay, so thank you. And thank you, Andrea and Alessandra, for the invitation. I love pizza very much, so it's always a pleasure to come back. So the topic of my talk is isoperimetric inequalities on manifolds with asymptotically non-negative curvature. So before entering the main results, let's just start with a brief, well, almost brief introduction on isoperimetric inequalities. So first, we start with isoperimetric inequalities in the Euclidean space. And it is well known that isoperimetric inequalities are in fact the quantitative version of a very old and famous geometric problem, which is the isoperimetric problem. So in its classical version, the isoperimetric problems ask, among all simple closed curves in the plane with a given length, which one bounds the largest area? Of course, the answer is known to everyone, and it is the circle. And as I said, the isoperimetric inequalities are the quantitative counterpart of this problem. To be more precise, given a compact smooth domain with smooth boundary in the plane, then the optimal isoperimetric inequality in R2 says that, let's see if, okay, the length of the boundary squared is greater than or equal to 4 pi times the measure of the area. And it is optimal in the sense that we also are able to characterize equality. That is, we have equality if and only if omega is a disk. So with this optimal inequality, we are able to solve, one is able to solve the isoperimetric problem. There is also a version of this inequality in Rn. And so you again take a compact domain with smooth boundary, and then the n-dimensional version says that the measure of the boundary to the power n is bounded from below by n times the measure of the unit ball times the measure of the volume of the volume to the power n minus 1 over n. No, n minus 1 here. And again, you have rigidity, so the equality is attained if and only if omega is a ball in this case. So you see that in order to solve the isoperimetric problems by using the optimal isoperimetric inequality, you need basically two ingredients. So you need sharp bounds on the maximum of the volume enclosed by the boundary of a domain. Bounds of this type are known as isoperimetric inequality. Okay, not the sharp ones, but just this kind of bounds. And then if you have an optimal bound, in order to solve the isoperimetric problem, you also need to identify the isoperimetric regions, that is the regions that for which you have the equality. So these are the two ingredients, but in this talk we will be only interested in the first one. So in understanding when a given Riemannian manifold actually enjoys an isoperimetric inequality. So this was the situation in the Euclidean space. What happens? What is known on Riemannian manifolds? Typically, there are two classes of assumptions under which isometric inequalities are known to hold on a general Riemannian manifold. The first one is when we ask non-positive sectional curvature and also that M is simple connected. This means that M is what is called a Cartan-Hadamard manifold. In this case, the isoperimetric inequality is known to hold on these kind of manifolds with optimal constant, which means the Euclidean one, if the dimension of the manifold is less than or equal to 4, while in general dimension, it is open. I mean, people think that the optimal constant should be the Euclidean one, but this is a very challenging and interesting conjecture. The second situation on which we know the validity of an isoperimetric inequality is a kind of opposite one, because it's the one where we have non-negative curvature. Actually, it suffices to impose that the Ricci curvature is non-negative to have an isoperimetric inequality, but you also need to impose some condition on the volume growth at infinity of your manifold. This condition is known in literature as positive asymptotic volume ratio. So you ask that at infinity, the measure of a geodesic ball of radius r over the measure of the Euclidean ball of radius r is equal to some positive constant theta. And actually, this condition is very important. Otherwise, you cannot expect to have an isoperimetric inequality. Just to have an idea, think of a cylinder, okay? There you can take as a domain, the one with boundaries to circles, which are orthogonal to the axis. And so you see that when your boundaries go apart, then the volume enclosed by them grows and goes to infinity. So you cannot expect to bound the volume in this situation by a constant that depends only on the length of the boundary. So this is a very important assumption. So I said that, okay, actually here in this talk, we will focus on the second setting. So when we have some non-negative curvature condition, the first one is another story. So what is it known about isoperimetric inequalities when we have non-negative Ricci curvature? Until the 80s, let's say, it was known that the isoperimetric inequality was true, but with the non-sharp inequality. And this fact can be, for instance, traced back to works of Kroc, combined with some work of Yau. Kroc proved a certain formula valid for any Riemannian manifold with a certain constant, and then Yau proved that when you have Ricci non-negative, you can bound, you have a specific bound on this constant, but not sharp. This was true until the 80s, let's say. until there was this nice, very nice paper by Agostiniani, Fogagnolo, and Mazzieri, who, among other things, proved the validity of the optimal isoperimetric inequalities in this setting via mean curvature flow, but with the dimension n equal to 3. And then, some years later, Brendel came and proved the validity of the inequality for any n with a completely different technique, which is by now known as ABP technique. So we will explain this technique in a moment, because it allows to do many things, actually, many geometric inequalities. But before that, so the two inequalities obtained there are optimal, and who are they? So you consider a complete Riemannian manifold with non-negative Ricci curvature, and again you have this assumption on the positiveness of the asymptotic volume ratio. Then for any bounded domain omega, you have the validity of this inequality. Where you see the difference between this one and the Euclidean one is the appearance of this theta here, which depends on the volume growth at infinity. Before explaining how Brendel proved this inequality, I focus on this technique because it can be localized, and we will see that it is very useful if you want to generalize these inequalities. But before that, let me just notice that actually in Brendel's paper, the isoperimetric inequality is proved under this form, let's say. I mean, it is proved on the validity of an L1 Sobolev inequality, actually. And then if you take h equal to 1, you deduce the isoperimetric ones. So it deals actually with this theorem. So every time I will, but on the other hand, it is known that isoperimetric inequalities are equivalent, in fact, to the validity of L1 Sobolev inequalities. So in this talk, we will just put the, I mean, we will just see isoperimetric inequality, but keep in mind that we also always have the L1 Sobolev counterpart. And this is interesting, and it also motivates the importance of the isoperimetric inequality, because L1 Sobolev inequalities imply LP Sobolev inequality, and these are a very useful tool if you want to do some analysis on manifold. So they are interesting also because of this, of that. Okay. So to understand how Brendel's proof works, let me just describe how this, what is this ABP technique, and how it can be used to obtain isoperimetric inequalities. So we will start from the very beginning. The first one who used this technique to produce isoperimetric inequality was Cabret some years ago. And this technique actually, the name is due to the mathematicians who used it for the first time, who are Alexandrov, Backelman, and Pucci. And they used it in a kind of different framework because they use it to have L infinity estimate on the solution of certain Dirichlet problems. So just PD. But then Cabret used this technique to prove the optimal isoperimetric inequality. Philosophically, the idea was to produce a deformation of your domain omega via a certain map that one has to identify. And this map has the property that decreases the isoperimetric ratio. So who is this map? The idea is that magically, the map that works is the gradient of a certain function, u, and the function u is the solution of this initial value problem. So is the Laplacian of u is equal to some function f, and imposes a Neumann boundary condition on the domain. Because of, I mean, in order to exist, this, in order to guarantee the existence of U, actually you are forced to ask that your function f is exactly this one with this boundary condition. And this map does the work. So how is that? A fundamental step is that you can define this set here, which is known as the lower contact set. The analytical definition is this one. And geometrically, it represents the points such that the hyperplane tangent to the graph at the point x lies below your graph. Okay, so this is why it's called also lower contact set. And the interesting thing is that the measure of this lower contact set via the map phi of U, the one that will decrease your isoperimetric ratio, simply by a change of variables, is this one. And then now your map is the gradient of the function U. And so this is in fact the Hessian. And so you can use the arithmetic geometric mean inequality, but your function U was very specific. It satisfied this problem. So on the right-hand side, you get your isoperimetric ratio. And now, to conclude, you need to prove that your, this is the right, this is the left-hand side, is in fact coincides with an Euclidean ball of radius 1 center at the origin. And to prove that, so you pick a point. This is the open unit ball. So you pick a point in the open unit ball. And then you call x the point in the closure of omega that attains, which is the minimum of this function, this auxiliary function that depends on p. Geometrically, this means that you have your graph, and you can consider these functions, which are hyperplanes depending on p, with some constant c. So your domain is compact. When c is close to infinity, your hyperplane does not intersect the graph, but then you can imagine to slide it up until it touches the graph in a first touching point. So your x is in fact the first touching point. But now you need to guarantee that, well, two things may happen. The point is either on the boundary of the domain or in the interior. And to guarantee that the point is in the interior of the domain, you use the Neumann boundary condition, okay? And now, once you have the point is in the interior of the domain, you are done, because this implies that by the definition, your point x is in the lower contact set. But it also implies, of course, that the gradient of the function up at x is 0. And this implies that the point p must be the gradient of u at x. This is wrong. This is phi of u of x. Okay, so p is in the image of the lower contact set through your deformation map. And this concludes Cabré proof, which is simple but very, very elegant. So how can we adapt, let's say, how can this technique can be used to produce isoperimetric inequalities on Riemannian manifolds with non-negative sectional curvature? So let's see which are the ingredients that can be taken as they are, and which are the ones that we need to change. So first of all, the idea is the same. We produce a deformation map, and this map should decrease the isoperimetric ratio. So we need to know which is the map in this case, and yeah, basically that, which is the lower contact set also. We can take the same solution, the same function u as in Cabré's proof. So what happens in Rn? The deformation map was the gradient, but you cannot use it in your Riemannian manifold because you want a deformation map of omega. So a map from omega to a subset of your manifold M. While the gradient, okay, here is a map from omega just because you are in Rn and you are identifying the tangent space with Rn. And the other problem we have is the lower contact set, because by this definition also requires that you are in Rn, because you are using here a lot of things of Rn, the notion of hyperplanes, the scalar products, and so on. So what Brundle did was to find the right substitutes, well, among other things, of course, to find the right substitute in Cabret's proof. So the deformation map now is given like this, so it is quite natural. Instead of the gradient, you introduce the exponential map, and you fix some r bigger than 0. We will be interested in the case where r is big, and you define your deformation map in this way. And what is the contact set in this setting? It's this ugly thing here, but just think that, so in Rn, you were considering the points such that the tangent hyperplane was below the graph. Here, morally, you are considering the points such that some concave paraboloid with opening 1/2r lies below, and specific vertex lies below your graph. So geometrically, this is the idea. Now that you know which are your deformation map and your lower contact set, you can try to reason as in Cabret's proof. So first of all, you can prove that you have this inequality, just a change of variables. So which are the difficult points now? Well, the first one is to know which is the image of the lower contact set under your map. And the other one is to estimate the Jacobian of the determinant of the Jacobian of your deformation map. So about the first one, Brundle was able to prove that, in fact, this set here that we denoted by dr, which is the set of points in M such that the ball centered at the point with radius r contains the domain, which when r is sufficiently big it contains some ball centered at a reference point, is contained in the image of this set. We won't go through the proof of this. The proof is quite technical, but just few comments. So you want to prove that if you pick a point P in the R, then you can find a point X such that P is the image over your through your deformation map of X. And the idea is similar to Cabret geometrically. So instead of so you minimize this function. So this means that you are coming from below with these concave paraboloids with vertex at P and opening 1/2r. And but the important thing is that here you are not using the curvature. I mean, you can prove it on any Riemannian manifold. Okay. And the point where you actually use the curvature is the second step. So when you want to estimate the Jacobian of the determinant of the Jacobian of the map. So we will see some details about this step in a moment, but just to conclude, I mean, the reasoning, you can prove that for any point X in the lower contact set, you have this estimate on the determinant of the Jacobian, but then since you have chosen U in this way, this implies that on the right-hand side you get this quantity here. And now if you combine step 1 and step 2, you can, for R sufficiently large, you come up with this inequality. And now what you do is you divide by R to the n on the left-hand side and on the right-hand side. Then you send R to infinity. then on the left-hand side is where you really need the asymptotic volume ratio, because the positiveness of the asymptotic volume ratio, of course, because that assumption assures that here you have this positive lower bound. And well, on the right-hand side, you just get this thing here. And this is your isoperimetric inequality in the case Ricci bigger than or equal to 0. As I said, the only point where the curvature is really needed is in step 2, so in this Jacobian estimate. So how do we get this estimate? So the idea is the following. You have your point x, you have your point in the lower contact set. You consider the geodesic starting from x with initial velocity gradient of u of x. Then what you do, you consider an orthonormal frame on the tangent space, and these the EIs are the vectors of this orthonormal frame, and then these capital I of t are the parallel transport of the orthonormal frame along the geodesic. Then another ingredient you need is these Jacobi fields, which are defined in this way. This is the differential of the deformation map. And these are the unique Jacobi fields that satisfy these initial conditions. And then you construct this matrix P, whose entries, Pij's, are defined in terms of your Jacobi fields and of your capital EI of T. Note that P is in fact the matrix associated to your linear map, which is the differential of the deformation map, when choosing the basis EI and capital EI. So if you estimate the determinant of P, you are able to estimate the determinant of your Jacobian. And that's what one wants to do. And in order to do that, you introduce this function here. And this function turns out to solve a Riccati inequality. And here is where you need your curvature assumption. So because if the curvature is non-negative, this thing here is less than or equal to 0. So you can integrate and you can get this nice estimate by integration. And looking at what happens when t is equal to r. So again, this is the only point where we need Ricci curvature bigger than or equal to 0. So this shows that somehow Brendel's proof can be localized. I mean, you can really see where you need the curvature. Okay. After Brendel's work, there were a lot of other works inspired by this one. Using the ABP techniques, some geometric inequalities were produced. For instance, it is quite natural to try to generalize these isoperimetric inequalities in a metric measure space with non-negative curvature in some sense. Here we have to say that when you are in a metric measure space, a smooth metric measure space, then there are different concepts of curvatures that you can consider. For instance, the first one that was considered by Jone, I don't know if the pronunciation, is this one. I mean, this is the so-called modified Bakry-Emery-Ricci curvature. The function f is the function that weights your measure. And so adapting to this setting Brendel's proof, if you assume that the modified Bakry-Emery-Ricci curvature is non-negative and the positive asymptotic volume ratio assumption is substituted by this one, where this thing here is the measure of the ball with respect to the weighted measure of the ball. Then you get this weighted isoperimetric inequality. But you have the appearance of this constant alpha, which plays somehow the role of a virtual dimension. So when f is equal to 0, you don't get the classical one in this case. Another possibility is to consider a different concept of curvature in this setting, which is, just the idea is to adapt Brendel proof, just replacing the Laplacian with the so-called F Laplacian, which is the right operator to work in this weighted setting, and the original measure by the weighted measure. But now there is another concept, as I was saying, of curvature, which is the Bakry-Emery-Ricci curvature, not modified. And this was really extensively studied in recent years because, as you know, it appears in the definition of Ricci solitons, so it was really important also in the Pereman conjecture of Ricci flow, the solution of Pereman conjecture via Ricci flow. But no, well, I said a bunch of strange things, but I mean, it's very important for Ricci solitons, why, blah, blah. Okay. So what we were able to do with Michele Rimoldi and Gianna Veronelli in a recent paper was to prove the validity of an isoperimetric inequality that now recovers the Euclidean one, the Euclidean one when f is equal to 0, assuming this curvature condition with the positive asymptotic volume relation condition replaced by this one. But you have there is a price to pay. You need also to ask some extra assumption on the function f. This is not surprising because every time you work with the Bakry-Emery-Ricci curvature instead of the modified one, you can somehow recover results that are true under the non-negative Ricci curvature assumptions, but with extra assumptions on the function f. So we were not surprised to need this assumption. And here is not like a direct adaptation because you also need to prove the inequality. You also need to modify the function y that you integrated in the Riccati inequality. And you end up with a different Riccati inequality, but you can work out things and you can prove the validity of this thing here. Okay. But now these are all, also the weighted isoperimetric inequalities are all in a setting of non-negative curvature in some sense. So one may wonder to ask what happens if we have some curvature, perhaps not like a small amount of curvature, but can we still say something? Can we say that the isoperimetric inequality still holds when adding a certain amount of negative curvature? So this is actually the problem that we want to face and to solve at least partially. Now, certain amount is really vague. It can mean anything. I mean, it can be that the negative part of the curvature is small in some integral sense, or also that is small in some spectral sense, that as we have seen in Marco Pozzetta's talk. Or it can also mean that the negative part is localized, that is, for instance, confined in a compact set, or that the curvature decays at infinity. So many things. And the problems that we are interested in is in the case where we have a spectral assumption on the Ricci curvatures, and also when we have a certain decay of the curvature. With respect to this last problem, a natural assumption to consider is when you are in a manifold with asymptotically non-negative Ricci curvature. What does it mean? It means that the Ricci curvature is bounded from below by minus a negative constant, negative function, minus lambda, which is a function which depends on the distance from a fixed reference point, is non-negative, is non-decreasing, non-increasing, okay? And it satisfies this integral assumption. We will call B0, B0 this integral here, which must be finite in order to have asymptotically non-negative curvature, which means somehow that your function lambda decays faster than S over 2. So under this assumption, actually, there was a partial result about the validity of isoperimetric inequalities. This is due to Donglin and Liu in 2004. So they assume that, the manifold that non-negative, asymptotically non-negative Ricci curvature, and again, positive asymptotic volume ratio. Then under this assumption, just, following the technique introduced by Brendel, they were able to prove this inequality. It depends on some things like this R naught, which is the, it depends on how far is your domain from your reference point, and also on this finite integral B1. This one is not really a problem, but the point is that in this isoperimetric inequality, there are two problems. The first one is that you don't want an inequality that depends on the domain. You want that the constant only depends on the geometry of your manifold. And the second thing that is not very nice is that you have here an extra term. And somehow, since manifolds with asymptotically non-negative Ricci curvature have many features in common with manifolds with non-negative Ricci curvature, you expect to not have this term. So the problem now, the other problem we want to partially at least solve is it possible to obtain a genuine isoperimetric inequality in case of asymptotically non-negative curvature? So in the rest of the talk, we will focus on these two problems. So about the first one, as I said, you have to choose which definition of small negative curvature you need to consider. And in the first result I present, we are working somehow with non-negative Ricci curvature in a spectral sense. So what we were able to prove is that if you consider a Riemannian manifold with dimension n bigger than or equal to 3, complete, and you assume that there exists a function phi, which is bounded, and bounded away from 0 and bounded from below, that satisfies this inequality. If you remember Marco Pozzetta's talk, this is a spectra. This is an assumption on the first eigenvalue of the Ricci tensor, actually, and with this constant n minus 2, which in his talk was 1 over gamma, I think. We are asking something more, because in their paper they were just asking that phi was positive, while we are asking it to be bounded. So it's actually a bit more. Then we also assume the positiveness of the asymptotic volume ratio. And under these assumptions, you can prove the validity of a genuine isoperimetric inequality, where you see that the constant depends on the dimension, on this eta, which is the upper bound of the function phi, and on the, as one may expect, on the asymptotic volume ratio. So as I was saying, so we saw on Monday why these conditions are interesting. They are very popular at this moment. And but also one has to say that this value n minus 2 is one of the value plausible for the function gamma to conclude that Ricci has pointwise non-negative Ricci curvature. That M has pointwise non-negative Ricci curvature. I mean, if you assume that M has more than 2 ends, then you can apply the result and conclude that the non-negativeness of the Ricci curvature pointwise. But at this point, since you are also assuming asymptotic volume ratio, you can conclude that you have the real isoperimetric inequality. So this means that, in fact, the theorem is telling really something when you have only one end, which is the case that was not included. So let me explain a bit how the proof works. So the idea is still something which is really popular at this time, to make a clever conformal change once you have the existence of this function. So what do? We call f the logarithm of the function phi divided by this n minus 2. And then, inspired by some recent works of Gilles Carron, Ilaria Mondello, and David Theodrose, we consider the manifold M, where you are conformally changing the original metric using this function f, but once you have made this conformal change, you are also weighting the new conformal measure, again by a weight that depends in this way on the function f. Now with this trick, you can prove that your new manifold, well, which is the old one, but with a different metric and measure, satisfies this condition. So it has a non-negative Bakry-Emery-Ricci curvature. And since your function here is bounded, that's why you need bounded, you can also show that you have the positiveness of the weighted asymptotic volume ratio. So now we have all the ingredients to apply our previous theorem, the weighted one. So you can conclude that with respect to this conformal weighted measure, you have this isoperimetric inequality. The constants are very explicit. They depend on this eta here, on the beta, which was related to the asymptotic volume ratio. And again, you have again eta. And now the conclusion is there because, again, you are considering f-bounded. So you can control the conformal weighted volumes by using you can control the original volumes and areas by using the conformal ones. Okay, and again, the constants are explicit. So this was the first result. We had in this direction of adding some negative curvature. And now there is a really nice characterization of manifolds that enjoy this, the existence of this function. Because as a consequence of work by Carron, it is known that when your manifold M is non-parabolic, this means many things. For instance, this means that the green function is positive. Then in this case, you can consider this function here, which depends on the green function and on the negative part of the Ricci curvature. This is called elliptic Kato constant. And if you guarantee that this constant is strictly less than 1 over n minus 2, so it's sufficiently small, then this is equivalent to us to guarantee the existence of such a function. So we have an isoperimetric inequality in this apparently different setting. And now what's the point? That if you are able to guarantee estimates from above for the green function, and you can balance these estimates with good decay for the negative part of the curvature, then you can guarantee that this elliptic Kato constant is sufficiently small. And in fact, this is the reasoning that led to this corollary of the previous theorem. In the same paper, we proved that if you assume that you have a complete manifold with only one end, then you assume a little bit more. You assume that the sectional curvature is asymptotically non-negative, okay, which is assumption 1. Then you can prove that if you have again the asymptotic value ratio, there exists a constant b tilde naught, which depends on the dimension and on the asymptotic value ratio, such that whenever your b naught here, which depends on the curvature, is smaller than this constant, so for b naught sufficiently small, you have a genuine isoperimetric inequality. So this is a genuine isoperimetric inequality in the setting of manifolds with asymptotically non-negative sectional curvature, not Ricci. So there is a price to pay. And you are also imposing that your manifold has only one end. And note that here I just put C, but C can be made explicit. It only depends on N, on beta, and on B naught. Okay, and moreover, you can check you can look at the dependence. How it depends on this quantity is quite clear, and you can verify that at the limit, so when this B naught tends to 0, you recover the one that you had in the non-negative Ricci case. And as I said, what you need to prove this is to guarantee that you have a good estimate for the green kernel. And under the assumption that M is complete with one end and with this curvature assumption, and also this one actually, this is done by Grigorian and Saloff-Kost. So then you can consider the right decay of the curvature and you are done. Okay. So this was the first result in the direction I mentioned, so proving isoperimetric inequalities when you have asymptotically non-negative Ricci curvature. But what is not really satisfactory, we of course, the constant is not optimal, so this is the first unsatisfactory thing. And the second one is that the validity of the inequality depends on how small is beta naught. Otherwise, you cannot guarantee the validity of the inequality with all this machinery. On the other hand, now we can look back at Brandel's proof of the isoperimetric inequality, and in particular at the only point where it needed the curvature assumption. That, as I mentioned, was when integrating the Riccati equation. So if you look at that, you see that actually you don't need that the Ricci curvature is non-negative on all the manifold, but just along the curve gamma. So, and the same is true if you deal with the situation where you have a non-negative Bakry-Emery-Ricci curvature, okay, with a different Riccati inequality, but same reasoning. So roughly, the idea is that, for instance, if you have this non-negative curvature in some sense outside a compact set, and you work with domains omega, which are in the complement of this compact set, if you can guarantee that your geodesic does not meet the compact set where the curvature is negative, then you can apply Brandel's machinery. And thence you can prove the isoperimetric inequality, at least for domains which are outside your compact set. On the other hand, it suffices to prove the validity of the isoperimetric inequality on the wall M, possibly with a different constant. This is a consequence of another result that we prove in a very recent paper in collaboration with Stefano Pigola, Michele Rimoldi, and Gianna Veronelli, where we proved that, well, something which was already known for p bigger than 1, for LP Sobolev inequalities and p bigger than 1. And we also proved that it is true when p is equal to 1, that is, if you have the validity of an L1 Sobolev inequality outside a compact set, then you can guarantee the validity of, again, an L1 Sobolev inequality, perhaps with a different constant, or for sure with a different constant, I would say, but in the wall manifold. And since the isoperimetric inequality is equivalent to the L1 Sobolev inequality, this tells that if you guarantee the isoperimetric inequality outside the compact set, then you can guarantee it for any domain on your compact domain on your manifold. So we pushed this reasoning a bit further, and we were able to prove actually the following theorem, which partially answered to the problem that I wanted to solve before. So this is a result on the validity on isoperimetric inequality with localized negative curvature. Why? Because we consider M a complete Riemannian manifold satisfying. So you have asymptotically non-negative sectional curvature, but you need to require, this is a mistake, this is a minus, but you need to require this minus n minus epsilon. You need to require a specific decay for the sectional curvature, which depends on the dimension n. So you ask for this condition on the complement of a compact set. You also ask the positiveness of the asymptotic volume ratio, but again, you cannot ask well, you don't ask it on the whole manifold, but you need to have a stronger assumption, that is to ask it on every end of the manifold, so on every complement of a compact set. If you assume 1 and 2, then you can prove that there exists a constant. Again, it can be made explicit, although it's very, very painful. But it depends on the dimension, on the asymptotic volume ratio, and on K naught, again, such that you have the validity of a genuine isoperimetric inequality. So you are requiring a bit more. You don't have the optimal constant, but you have the validity of the nice isoperimetric inequality. And this is quite satisfactory, at least for me. Note that it's very important to ask the condition on the ends and not on the whole manifold. Because, for instance, if you imagine to ask it on the whole manifold, think of the connected sum of Rn with a cylinder. Okay, so you have the asymptotic volume, the positiveness of the asymptotic volume ratio on the whole manifold, but you cannot have the validity of the isoperimetric inequality in the cylindrical end. So we need to strong this assumption. So this was the last result, but to conclude, let me just say a few words about the proof. I mean, the main ingredients and how they are used. First, the assumption on the sectional curvature, and in particular that decay of the curvature, are needed because when you assume that, you can guarantee the existence outside a compact set, a certain compact set, of a function phi, which is bounded and which is a solution of the inequality that we have seen before. So now the idea is to define this function f exactly as before, as in the spectral case, and to consider exactly as before this function, this manifold M, with just conformally changing the metric and weighting the conformal volume. So now the point is that outside your compact set, you are in the same situation as before. That is, you have non-negative Bakry-Emery-Ricci curvature and asymptotic volume ratio. So if you, okay. The other thing, which follows from the theorem that we have seen before, is that actually you need to prove the isoperimetric inequality only for domains which are outside this compact set. So if you are able to guarantee that your geodesic does not enter the compact set, then you are done. But this is not true in general, okay? And this is the difficult part of the talk, which is very technical, so I won't spend much time on it. Just the idea, this thing here is not written well, so don't look at it. The idea is that when you impose the assumption on the curvature, the asymptotically non-negativity of the curvature, then you have a very rigid structure at infinity. And this implies that in general, you cannot guarantee that all the geodesic do not enter the compact set. But you can choose some points in the image of the lower contact set through your map, such that the geodesics from X to this point do not enter the compact set. So you consider a smaller set instead of the one in the Ricci greater than or equal to 0, okay? In this case, if you make the right choice, and this is the very technical part, you can guarantee that all the geodesics that start from some point X in your lower compact set, and it arrives to a point which is in the image, does not enter your set K, where you have negative curvature, okay? Now the problem is that in order to conclude and then to have the isoperimetric inequality, you need to guarantee that the measure of this set is non-zero as r goes to infinity. And again, this is a very tricky part, and you can do it again using both the assumption on the curvature and on the asymptotic volume ratio on any end. So, and in this case, you are able to bound the dimension of this restricted set of points P in the image by a constant, which depends only on B naught, on the IVR, and on N, times Rn. And now, once you have this thing, you can perform, you can use Brando's machinery or the proof that we made in the spectral case to conclude that you have the validity of the isoperimetric inequality outside your compact set. And then you conclude about the whole manifold, as I mentioned before. So this is roughly the idea of the proof. And the results are contained in this paper. And I thank you for your attention.
Was very clear. Are there questions?
Yeah, thanks for the nice talk. I have a question about the hyperbolic case, actually, which is not in your setting because of, right, it's clear, but you have this Riccati equation becomes then still a very clean ODE. So can you then do do the Brendle proof in this hyperbolic?
No.
Why?
Because you have problems when passing to the limit with R.
Okay.
I
So
mean,
you really need this Ricci term to be almost positive. So.
Yes.
Okay.
We try to do that.
Okay.
But
right. Thank you.
okay.
Other questions? Yes.
Thank you for the talk. I was just curious to understand whether you still expect that some isoperimetric inequalities like this with asymptotically non-negative curvature could hold only in terms of the Ricci curvature and not involving the sectional.
No.
Okay.
I mean, that's my feeling, because usually there are okay, sometimes you need to add an extra condition at least. Okay, in the same paper, in the first paper, actually, we prove a version with the asymptotically non-negative Ricci curvature. Okay, but we need to require more on the decay, like the n plus epsilon decay. But you also need to add an extra assumption on the volumes, which is called VC condition. I don't remember how to state it, but so without that condition, I'm not sure that you can. I mean, I don't think you can prove the validity of the inequality.
But then you can.
With that condition, perhaps yes.
So you can sort of replace the assumption on the sectional with something on the volume.
There are many papers where the assumption on the curvature is replaced by Ricci plus this one, which is automatic when you have the assumption on the sectional curvature. So yeah, the answer is in that case yes, but in general without that assumption.
Okay, makes sense.
Yeah.
Okay.
Okay.
Thank you.
Other questions? So if not, we thank all the speakers of this morning.
Welcome back to the afternoon session. It's a pleasure to introduce the next talk of today by Carlo Sinestrari of University of Roma Tor Vergata. The title of the talk is Volume Preserving Curvature Flows in Euclidean and Riemannian Spaces.
So thank you, Mattia. Thank the organizers, Alessandra and Andrea, for first organizing this beautiful conference and also for having me here. I'm very glad to participate in this event and to be in Pisa. In this talk, I will basically speak about two different results. The common feature is that they both are deal with volume preserving mean curvature flow. The first one is a result in collaboration with Liang-Jun Wang on in the capillary case. It will have contacts with what Julian Scheuer talked about this morning. And it will be a flow by powers of the mean curvature. And in the other part of the talk, I will speak about joint result with my former PhD student Jacopo Tenan on mean curvature flow of two-dimensional surfaces in a three-dimensional asymptotically flat space of the general relativity. So the common thing is the volume preserving curvature flows in both cases. And maybe another thing I would say in both cases, it deals with convex hypersurfaces. And this is the structure of the talk. I will say some general facts about volume preserving in curvature flows. Then the first part will be about this capillary flow with general powers of the mean curvature. And the other part will be that mean curvature flow, so without powers, but in asymptotically flat spaces. So in my setting, so M will be the ambient space, which I say general Riemannian manifold. This will be just for the second part of the talk. In the first part will be Euclidean. Then sigma T will be my evolving hypersurface, so immersed, embedded in M. Nu will be the symbol for the normal vector. H, the symbol for the mean curvature. I consider, to begin with, a general power alpha of the mean curvature. I consider the flow where each point moves with normal speed given by power of h. And I focus on the volume preserving modification, so that in the speed we add a term given by the average of the other term. So the average of the two terms together is 0 and the volume remains constant. So on some easy remarks that are probably very well known to most of you. As I was telling, the domain enclosed by the surface has constant volume. Probably all also know well this flow is different from the rescaling of the mean curvature flow you sometimes see when you rescale near a singularity in order to keep volume or area constant. You can define volume preserving in many ways, but so some modifications are just a rescaling. So you see better what's happening, but you do not change what's happening. But for in this kind we are looking at now, the two flows are substantially different, although they share some properties, some results. So, and in fact, we will see some different behaviors in certain situations. A very nice fact, which is valid for the alpha equal 1 case, but also for general positive alpha, is that while the volume is constant, the area is decreasing. If you compute the evolution of the area, you find this expression, so difference between integrals involving power of h, and it's easy exercise with Hölder inequality or Jensen inequality to show that this is has a sign, is negative with the strict inequality unless h is a constant function. Therefore, the area decreases. You can, since the volume is constant, you can also say that the isoperimetric ratio improves, which is not the case for the standard mean curvature flow, which I found at the beginning a bit surprising because mean curvature flow is the gradient flow of the area functional, but is not necessarily the isoperimetric ratio is not necessarily monotone decreasing. So this property is good. This means I wrote an informal statement. If you have enough good estimates to show that, let's say, the curvature becomes bounded, so you don't have finite time singularities, you have long time existence of the flow. And so if you have enough estimates, you also have compactness, so you have at least up to subsequences convergence to something. And then this monotonicity property implies that this something must be CMC. CMC means it is a sphere, and if you have a unique possible limit, then this would usually imply that the whole flow converges to this limit. So this is a general strategy that one can expect for this flow as long as one has enough estimates, which of course are not may not be available. It depends on the situations. On the other hand, compared to the standard mean curvature flow, the presence of this small h term, which is global, it's such that some well-known properties for the standard mean curvature flow no longer hold here. For instance, the avoidance principle that two disjoint surfaces remain disjoint during the flow is in general no longer true. Actually, you're probably familiar, but I wrote a simple example. Let us consider, for instance, curves in the plane. It could be done in general dimension. Consider the blue curve and the green curve. So the blue curve has a change in curvature. So in the flat part, the curvature is zero, so but the average is positive, so the flow will go outwards. Instead, in the curved regions, the curvature is larger than the average, so it will flow inside. On the other hand, the green is constant curvature, so it doesn't move. So the green does not move. The blue flows inside in that part where they're very close, so the avoidance principle does not hold. In fact, if you try to apply the usual argument you would use without the small h term, you see that when you want to apply the maximum principle, you find two solutions of the same equations except for this h term, which is different for the two solutions, and you cannot compare at a single point just from the information that is the first touching point. On the other hand, okay, I don't know why it's like this. On the other hand, something that uses the maximum principle that can be applied in this setting is the Alexandrov reflection. This was introduced by Chow and Gulliver in a series of papers, and there are various versions. But this one is very nice and powerful. It is. Let me draw a picture. Well, suppose you have your hypersurface, and you have a hyperplane, and well, you consider this part to be positive, this other part to be negative, and you consider the reflection of the positive part on the other side. Well, you see that the surface reflects strictly across this hyperplane if this part is strictly inside the enclosed region. Plus, there is some transversality conditions that they should not become tangent, but I do not go into details. And the Chow-Gulliver result just says that if this holds at a certain time, it also holds at all later times. This holds for any parabolic curvature flow. And And it also holds if there is a non-local term, because when you consider the surface and the reflected one, they have the same h. So when you want to apply maximum principle, you compare two solutions of the same equation with the same h. So the normal vectors point in the right way to apply the maximum principle. So this holds also for the volume preserving flow, for instance. And the consequence is the following. So it's not very relevant for what I will say minutes, but I think it's interesting. It's very easy. There is a well-known property of the standard mean curvature flow that if you start with a there is a property that one is used to for standard mean curvature flow, is that if you have something compact, you know that it will remain inside the compact region because you compare with a sphere. The sphere shrinks, so also everything which is inside the sphere will remain inside the sphere. So for volume preserving mean curvature flow, this may no longer be true. So if you start with something bounded, you don't know it will remain inside the bounded region by the same argument. But you can use Alexandrov reflection to show this if you have a diameter bound. If, for instance, like you often have in the volume preserving case, if you know that, if you're able to show that the evolution of your surface will have a bounded diameter, then you can prove that this surface cannot drift too much during the evolution. You take any plane which which does not touch the surface, and so this is a trivial case of the reflection. I mean, if you take this, what is this? So, I mean, what is on this side reflects well because it's empty. You have nothing to reflect. So this means that it will remain like this. And in particular, this means that you cannot have at a later time that it has gone on the other side, because if all the surface is on the other side, then trivially it does not satisfy. So the reflection will not be inside. So you cannot have this picture. If all the surface is on one side of a hyperplane, it cannot pass on the other side of the hyperplane. So if you have no control of the diameter, then this thing can become larger or longer. But if you have diameter control, this means that if this cannot happen, then this cannot move too much. It remains inside the compact region. And this is an argument we will use in a theorem I will talk during this talk. So let me give a very brief bunch of examples of convergence results for the volume preserving mean curvature flow. The first results are for convex hypersurfaces in Euclidean space, which are due to gauge for the curve shortening case and by Huisken for the general case. Then there are other kind of results. There is a paper by Escher and Simonet where the surfaces are not necessarily convex, but are a small perturbation of a sphere in a norm, which is not exactly C1 alpha, but something very similar to that. And with the same type of norm, it was done in Riemannian manifold, but for initial data which are close to a small geodesic sphere around the point by Alikakos and Freire. And then there is a paper by Esther Cabezas-Rivas and Vicente Michel on the for H-convex hypersurfaces in the hyperbolic space. Some other thing, there is no systematic analysis of singularity as in standard mean curvature flow, although one expects that it should develop similar singularities, that the small h term should not affect substantially the asymptotic profile. And also in recent years, there have been a lot of activity also by many Italian authors about weak solutions, level set solutions of volume preserving mean curvature flow. This is probably the first paper, but there are many others more recent. Okay. So the previous slides were for power 1. And when one wants to study general power, then the situation changes a lot, because the classical tool that is used, at least in some of the papers I was quoting, for showing convergence to a sphere is what's called the curvature pinching, so that the principal curvatures which are positive on a convex surface have a bounded ratio, so the largest divided by the smallest cannot become too large. This was this technique basically goes back to the pioneering paper by Wisken in the standard mean curvature flow. But for general power, the curvature pinching, so it's more difficult to prove, but actually Ben Andrews has showed that it cannot be expected in general, that you cannot, so you expect it somehow anyway, but not in a monotone way. So you expect convergence to a sphere, at least most of the time, but not with a pinching which is monotone. So one needs other ideas, other techniques. For the power of the mean curvature, there was the PhD thesis, I think, by Felix Schulze, who showed if you start with convex, not written it here, then you still have that it shrinks to a point. It does not create singularities. There are no neck pinch singularities, but it shrinks to a point, but you don't know that it becomes round. It can shrink to a point, but maybe more and more eccentric. And in fact, for instance, if in the curve case, if alpha is 1/3, there is a fine invariance, so that ellipses are homotetical solutions. So it is not true for general powers. At least one expects that for small powers, there is not convergence to a round point. And Schulze proved convergence to a round point for powers higher than 1, but with stronger assumptions on the initial value, not just convex, but with some strong curvature pinching, that the ratio between different principal curvatures is close enough to 1. And instead, in this respect, the volume preserving flow has a better behavior, at least easier to study. So for any power, there's this result of mine which showed that one has convergence to a sphere also by a relatively easy technique using tools from previous results. That for any power, convex hypersurface converge to sphere. So of course you don't have to rescale in the volume preserving case. And I don't say the details of the proof, because the strategy of the proof is what we adapted with Liang-Jun Wang in the capillary case. So let me describe the setting, which is the same setting, I think also more or less the same notation that Julian Scheuer used this morning. So we have a sigma is a hypersurface, this time with boundary. So the hypersurface is contained in the upper Rn plus 1, and the boundary is instead in the horizontal plane with height 0. And we want to consider a family of surfaces which keep these two constraints, that the boundary is in the horizontal plane, and that there is a fixed given contact angle along the boundary, which is given by certain theta. And in principle could be any angle between 0 and pi, but also here I will soon restrict to theta between 0 and pi half, so having an acute angle here. And we want to consider the similar evolution to have a flow by powers of the mean curvature. And again, in a volume preserving way because it's actually easier to study. But you see, we have to adapt the flow, because if we flow in normal direction, then these points would just no longer belong to the horizontal plane. So we modify it in, let me first say this. This is everything I learned from my co-author, who is much more expert on this kind of capillary problem. For me, it was a new topic. So it's natural to define a modified isoperimetric ratio. So sigma hat is the enclosed region, so it's the n+1 dimensional region, so between the surface and the flat side. And instead of making area divided by volume, we subtract a term with the area of the flat part multiplied by this factor. So this is positive, but in this way it has a better behavior, and it is possible to prove isoperimetric inequality that is this quotient is minimized if and only if sigma is a spherical cap. So is the intersection of a sphere of any radius with the upper half space with the correct angle, with the angle theta on the boundary. And so it's in order to consider a flow, it's good to modify the normal. And so instead of considering the normal, we add this correction in such a way that on the boundary of our surface, it becomes horizontal just by the capillary condition. And then we consider the volume preserving power mean curvature flow, where instead of having the usual normal, we put this modified normal. We keep this Neumann boundary condition, and then so local existence follows from standard techniques, and we want to see if we have convergence to a CMC limit, so to a which would be a spherical cap. And the answer is yes. We have to consider an angle between 0 and pi half. Then just like in the standard closed case without boundary, convexity is preserved, and there is a long time existence and smooth convergence to a spherical cap. A couple of remarks. As in the talk of this morning, the case P half would not really be something new, because one could reflect across the hyperplane and reduce to the closed case. So it would not be new. And in this case, if the restriction is violated, so on one hand, some of our techniques do not work, but I would also expect that the result would not be true, because one could think of a surface with a very tiny touching part, and it may be that if this is very thin, then one has a neck pinch on the touching side. So maybe it would still be interesting. Maybe there is an smooth evolution without boundary afterwards, but it would be a different story. I mean, so in this case, we think that this restriction is essential in order for the result to be true. Okay. So let me say something about the proof. So the invariance of convexity follows by somehow well-known techniques, but which have had only recently adaptation to the capillary setting. So we use a tensor maximum principle, which in its first version comes from in a paper by Hamilton. It was generalized with an additional helpful term by Ben Andrews in the closed case. I think there was a old maybe PhD work by Axel Stahl where some maximum principle with capillary boundary was also present. And then there is this general version by these authors that we have used to show that convexity is preserved. Well, as soon as one has convexity, of course, this means that mean curvature and second fundamental form control each other. So a bound on the speed is enough to give a bound on the whole second fundamental form. And so another feature of volume preserving mean curvature flows is that this non-local term has somehow a wrong sign, so plays a mild bad role in the preservation of convexity, because it does not prevent convexity on finite time intervals. But in principle, when you look at the equation, it may happen that the convexity slowly deteriorates with time, so that if, as we wish, we can show that there is global existence, when we go to infinity in time, the convexity may become weaker and weaker. And since in this case we have a nonlinear diffusion coefficient, if alpha is different from 1, this would either go to 0 or to infinity if h goes, if the infimum of h goes to 0. And this could potentially create a problem in the analysis to obtain uniform regularity estimates. And therefore, we have to show that this does not happen. But that's what we do. And this is the main idea that can be used in the volume preserving case that is not available for the standard mean curvature flow. We have also here the monotonicity of the isoperimetric capillary isoperimetric ratio. So the volume is preserved, and these other quantity, this energy, so that this difference of areas instead is decreasing. So the quotient is non-increasing. And this gives geometric constraints somehow. If you have that the isoperimetric ratio is bounded, this means, roughly speaking, that your solution cannot become arbitrarily eccentric, arbitrarily elongated, so too far from a sphere. And this can be stated quantitatively in terms of inner and outer radii, which in this case, inner and outer radii would be the radius of spherical caps you can put inside and outside. So we have our surface. So we can maybe can try to write it a bit more irregular. Okay. So we can find this should be exactly spherical, so that the largest spherical cap I can find below. So this would be the inner radius, and then the smallest spherical cap I can find outside. Well, and we can show that the ratio between the two has to remain bounded because of this monotonicity of the isoperimetric ratio. And this is somehow the replacement for curvature pinching. We have radii pinching, which at first seems weaker information, but it's enough for our job because knowing that the ratio is bounded, knowing that the volume is preserved, this means that they cannot both go to zero or to infinity, so it means that each of them separately is bounded. And this allows to use a well-known technique, which is, okay, okay, so this is the part that we have pinching of radii. So it was it uses ideas that were already present in the setting without boundary. And yeah, as I was telling, this allows to use a well-known technique called Cho trick, because he was the first author to use it, that gives a bound from above on the speed. And it turns out that in the volume preserving setting, there is a version with the opposite sign that also gives a bound from below. And this is everything we need to have these regularity estimates needed for having long time existence and convergence to a CMC limit. And also for this class of capillary hypersurfaces, there is an Alexandrov theorem saying that if it is CMC, then it has to be a portion of a sphere. Okay, so this was the first result I would like to talk about, and yeah, hope I'm not putting too much stuff in this talk in this post-lunch time. But so the next result is in a different setting, so forget about what we're discussing until now. And so now I no longer consider a general power, it will just be mean curvature, volume preserving mean curvature flow. Also, the dimension will be fixed because we consider the application to time slice of a Lorentzian manifold in general relativity. So we have a space-like time slice, which is supposed to model an isolated gravitating system. So one has something possibly complicated in a compact region, but as you the further you go away from the compact region, the more the metric approaches the Euclidean one. And so physically, the ambient space will be this three-dimensional Riemannian manifold. And so our evolving hypersurface will be a surface with 2 dimensions. And the starting point, the inspiration for the result I will describe you now, is a classical paper by Huiscan and Yau, where the setting was an asymptotically Schwarzschild 3 manifold that is the metric, so outside of a, so the manifold disregarding some compact region is diffeomorphic to the complement of a ball in R3. And so in this, we have a standard choice of coordinate inherited from R3. In these coordinates, the Riemannian metric of M is, has a leading order term, which is the standard Schwarzschild metric of mass M, positive. And there is a remainder, lower order term, which satisfies these decay assumptions. So this was a pioneering paper where the assumptions were somehow strong. So there are 4 derivatives and there is a strong decay. The purpose of Wisconsin was to construct a CMC foliation of the outer part of the manifold, and they did it by using volume preserving mean curvature flow, just because if it exists for all time and if it is regular, then it yields as a limit a CMC surface. So the result was this one. Consider the volume preserving mean curvature flow with initial value Euclidean sphere. So what in these coordinates would be a Euclidean sphere, of course, in the Riemannian metric, also in the Schwarzschild metric, it would be a CMC surface, but we have here additional terms. So we start from something which is approximately CMC, but not really. So we let it flow by the volume preserving mean curvature flow. And then with Konoya, we're able to show that there is global existence, convergence to a CMC, well, I should say surface, it's just two-dimensional, stable. So the second variation of area is positive. And for large enough radius, the family of these limits form a foliation of the outer part of the manifold. And this is different from the Euclidean case because of the presence of the positive mass. In the Euclidean case, you have the spheres, but you can translate the spheres. You cannot distinguish one sphere from its translate. So if you do something similar in a Euclidean case, if you take a family of almost a CMC surface and you let them flow and you go to a CMC limit, it's not clear that you find the canonical limit because the limit is unique up to translations. But the point here is that the non-Euclidean metric with positive mass breaks the translation invariant, so the CMC limit for a given radius is unique. And so this has interesting application because it allows to define a geometric notion of a center of mass, which in most cases is equivalent to the coordinate based definitions that were available in the literature. It's interesting to compare different notions in some limiting cases, and there are also some problems with Wisconsin definitions that have been dealt with in more recent works that I will mention later. And let me mention this, it's independent on the rest of the talk, that Wisconsin also showed that the CMC surface obtained as a limit of the flow is unique among all possible CMC surfaces which are outside a given compact region. So characterizing the uniqueness of CMC surface is a difficult and interesting topic that there are uniqueness and counterexamples depending on the hypothesis in many papers by these authors in different combinations. I'm not giving a detailed list of references, just mention them shortly. Okay, so maybe I skip this. And so this Wisconsin result was so attracted a lot of interest, and there have been since then many. So the first is the same result with a different technique, and the others are generalizations under weaker hypothesis. And well, maybe so I don't enter too much into details. Roughly speaking, in all these works, the hypothesis on the metric is that It's not necessarily asymptotically Schwarzschild, but it's generally asymptotically Euclidean. So it's no longer required that the leading term is Schwarzschild. And so the symmetry has been weakened. Schwarzschild is spherical symmetric, and this is no longer required in the latest works. And also the decay rate has been weakened up to some optimal assumptions. The one that were first obtained in the paper by Nertz, who showed that the hypotheses in his papers that are the same ones that I will write in following slides are somehow necessary and sufficient to, roughly speaking, to have this foliation. And all these works in the previous slide have the common feature that use a different technique by Wiscombe and Yao. They do not use a flow. They use methods like implicit function theorem or continuity method or Lyapunov-Schmidt reduction. What motivated our work is, can one prove the same result by the original approach, by a flow method? So if we consider the same flow as in Wiscombe and Yao, but in the more general setting, say as in the paper by Nertz, would the flow have the same behavior? So heuristically, it would seem an easy problem. I mean, we know that the foliation exists. The flow, so we have, for positive mass, we have a family of stable CMC hypersurfaces, and we would think if we start close to these hypersurface volume, an area decreasing flow can only converge back to CMC hypersurface. But of course, we don't want to really use the existence of the CMC foliation. One could probably obtain a trivial result by taking something which is very close in C4 norm to a CMC surface, then it would converge back to the CMC surface. This would not be interesting. We want to not assume that we want to do something independent from the other papers. So an independent approach that can prove the existence of the foliation and also prove the asymptotic behavior of a fairly general class of almost spherical initial surfaces. So I recall the assumptions of asymptotically flat. These are the same assumption as in Nertz. Maybe I don't read them in detail. It's, if you are familiar with the setting, they're pretty standard. But you see, a point that I would like to point out is in these earlier works, the decay concerns the metric, the derivative of the metric, and the second derivative, that is the Ricci curvature. Whereas people don't like to have some decay assumptions on the derivatives of the curvatures because they have no immediate physical interpretation. So we assume that everything is smooth, so the curvature possesses as many derivatives as we wish, but we do not make a priori assumption on how fast they decay to zero as we go to infinity. So the derivative exists, but we do not make decay assumptions. We assume that the mass is positive. This is something we cannot avoid with this approach. And so let me recall a bit of notation. Something is like in the first part, we have sigma, which is our surface. We call lambda 1 and lambda 2 the principal curvatures. As it is customary in some of the literature, I call H the mean curvature, capital A the second fundamental form, but I will call small h instead of small a, the components of the second fundamental form. An important ingredient is the traceless part of the second fundamental form, which measures how far it is from umbilic. Our aim is to show that this is zero. We want to show that it converges to something round. Another important notion is the barycenter, so the mean value of the position vector. And the area radius is this number that on a Euclidean sphere would be the exact radius, and otherwise it's something that gives us information on the scale of our surface. And so the strategy is to introduce a class of surface which are approximately round and CMC, so that we want this to be small and this also to be small. We want that lambda 1 and lambda 2 are close to each other, and the h is almost constant with a very small gradient. And we consider the requirements in an integral form because it will be easier in our setting to obtain integral estimates instead of sup estimate. And another important information we need on our surface is that center of mass is not too far from the origin. We allow some movement, but it should be of lower order. So sigma, forgot to say, is the scale parameter, is approximately the size of the radius. So a surface in this class, you should think of it as approximately a sphere of radius sigma. And in fact, the Euclidean sphere belongs to this class for appropriate choice of the parameters. And so a difference, so Wisconsin had already a class of round surfaces. It is also present in the work by Nertz. But in the previous works, it was defined by pointwise conditions. Here we use integral conditions. This is just a matter of it's practical for the estimates because, in fact, well, maybe I'll skip the first remark. The second one is more important, that these integral estimates, in fact, imply pointwise estimates. There is this result by Nertz, which shows that if these two quantities are enough small, and these two quantities occur in the definition of our class, then we can derive bounds on these quantities, in particular on the L infinity. We have also pointwise bounds on this. So lambda 1 and lambda 2 are close to each other. So we have a hidden pointwise regularity of our surfaces, so closeness to a sphere. And also there is a theorem by Delelis and Müller showing that this L2 bound on the traceless part of the second fundamental form, which we assume is implies more than it tells. So imply also, so this in principle implies that at each point the principal curvatures are close to each other, but their result shows that then they are also close to the same value at different points, so that the whole surface is actually globally close to a sphere. So maybe I will just say it very quickly. The strategy will be to show that for a suitable choice of the initial data and of the parameter, the flow never leaves this class of round surfaces. So we have control on how close it is to a sphere and on how the barycenter remains, can at most go far away from the Euclidean center. And maybe, Yeah, there is one part about the curvature estimates. So this is probably the most interesting step. We want to show that this quantity remains small. So there is the evolution equation that was already present in Wisken and Yao. So you see in the equation there are these gradient terms. So Wisken and Yao had the decay assumption that allowed them to use the maximum principle. Here instead we do not have a good bound on this quantity, but the idea is to integrate the equation, so to estimate the not the L2, we will estimate actually the L4 norm of this. And then when we integrate, we can let these derivatives disappear by integration by parts. And so the idea is that we have one good term, this one, and observe this good term contains the small h. So again, the volume preserving mean curvature flow gives some additional help with respect to the standard mean curvature flow. This turns out to be higher or lower order, so stronger than all the other ones. And it gives a negative contribution. So let me skip these details. And so by these so a series of integral estimates, we show that all the properties of the roundness class are invariant. The only one that's missing, because it's a completely independent one, is the bound of the barycenter, that the barycenter cannot drift too much. We cannot use Alexandrov reflection because this requires Euclidean, or at least space form. It cannot be easily done in a non-flat setting. And so maybe I'll just have time to show this. So the key quantity we look at is just this one. So when we do first variation of the area, we find this expression. So the L2 norm of h minus its mean value. And this quantity, h minus small h, is also the speed of our flow. So this term somehow also controls the possible drift of the barycenter. So let us derive once more. And this also has a nice expression. We have two terms. So one is a reaction term that can be explicitly written, and this can be written in terms of this operator L, which is the well-known stability operator. And well, I don't have time to say the details, but the stability operator has been widely studied in previous works. And basically, Nertz and so with more details in a more recent helpful work by Sedebam and Sakovic. Basically, L is a positive definite, which is good for our purposes because we want a negative sign here on CMC surfaces. Our surface is only approximately CMC, so we have an extra term, an error term, which at the first sight seems too large, but it turns out that due to some symmetry properties, it is nevertheless possible to estimate everything. And so we cannot find bounds on this. So let me just go to the conclusion, which is this one. That is, we have what we wish, so convergence, large time existence and convergence to a seam surface, if the initial value belongs to our roundness class, and we have to make that was, yeah, -2 minus epsilon. There was a fraction that was not intended to. So this should be -2 minus epsilon. We have to know this additional information on the initial value. HT is what's in this context is called the translational part of the mean curvature. So it's the projection of the mean curvature on the eigenspace of the basically the three translational eigenfunctions of the Laplacian. And so to be more explicit, which kind of initial data have this satisfy this condition? The spheres, so the kind of initial data which were used by Wisken and Yau, satisfy this condition, so have the same properties as in Wisken and Yau if we had somehow weak symmetry assumption. This kind of antipodal symmetry, approximal antipodal symmetry is known as Regge-Teitelbaum condition. We only have to assume it in a weaker form than it is usually done, but still we cannot completely make it for Euclidean spheres in general asymptotically flat setting. We have to add this asymptotically flat condition. In this case, we are able to show that the flow converges to CMC limit. And maybe I don't show the slide. This is a collaboration with Jacopo Tenan, who has then also generalized this construction to space-time mean curvature, which is more complicated from an analytical point of view, but somehow one can rely on the CMC foliation of the space-like setting to have a better initial data that compensates the additional analytical difficulty and allows to have convergence also in that more general setting. So I apologize for being a bit longer, but I thank you for your attention.
Thank you, Carlo, for your talk. Are there questions from the audience?
Thank you for the nice talk. And this is a very basic question for sure. But in the capillarity problem, the thing is, okay, what was the problem? Okay. When we, I don't remember. Okay, I'll ask you later. I don't. Okay, I forgot. Okay, there was a problem. I don't remember.
You can try again in a way.
No.
Okay. Okay. Other questions? Okay. In fact, okay. So there's one here.
So for the previous slides, so do you mean the CMC foliation exists without, for the general asymptotic assumption, without like a Regge-Teitelbaum condition?
Sorry.
Facciamo un comma piccolo, per favore. Sì, grazie.
Sì, questo per il pubblico è... Bene, bene.
Well, so without this assumption, we are not exhibiting an explicit example of initial data which satisfies the necessary, not the necessary, the sufficient condition for the conversion. It's something maybe similar to. It's something similar to your paper, because you also in your previous paper you do not work with spheres. You make a first step where you improve the spheres, and probably we could do something like that. So in order to have an explicit example without the Regge-Teitelbaum condition, we would need a first step where we improve the sphere to something which has a smaller translational part of the mean curvature. So but we somehow wanted to use only flow techniques, so we didn't try to make an explicit examples by this by this technique.
Grazie. Arrivederci.
Without the vegetable condition, the berry center can drift, right? So is that your class of the B sigma or class of surfaces where the volume preserving mean curvature flow stay? Does that capture the property the berry center may possibly drift to infinity?
I mean, so it seems that it could drift to infinity. So in order to prevent it, we need to postulate that that on the initial value the mean curvature has this stronger property to have a small translational, slightly better estimate than what we usually assume for our class.
Thank you.
Oh,
Thank you so much.
thank you.
Are there other questions? Okay, so if not, we thank Carlo again. We can finally resume with the next talk by Mariel Saez. Talk is about the classification of gradient K Yamabe solitons.
Well, thank you very much, and thank you everyone for waiting. Thanks the organizers for having me here. It's been an amazing conference, despite the latter technical issues. I'm going to talk about a geometric flow, and I'm going to talk about the soliton solutions of that geometric flow. I'm somewhat new to the flow, so there may be things that I don't know, but let me first tell you what the flow equation is. So we're going to take a manifold M and a metric G0, and this is a conformal flow. So I'll be thinking about metrics of the form, let me call this GU, some function U. Okay. This is gonna depend on time, times the function, times the metric G0. And the flow that I'm gonna be studying today is gonna be, oops. The time derivative of this is gonna be equal to the sigma k's are similar to the ones that appeared today in Julian's talk, but let me explain in a minute what they are. Times G. And here I need to define what all these things are. And hopefully after defining, I can motivate why we wanna do this. And here, let me maybe make sure I don't mess up the numbers. And I think the microphone, I mean, I'm going a little bit Darth Vader, I think, but we'll see. So here, AG is the Schouten tensor. Which I always mess up the constant, so that's why I want to copy it. So AG is going to be 1 over n minus 2, the Ricci tensor, minus, again, a number that I don't remember. This is the scalar curvature, over 2n minus 1, times G. And sigma K is going to be, I think, Julian sort of very cleverly avoid defining too much these things, but I think I'm not as clever as he is. So okay, so here K1 to Kn are the eigenvalues of G minus 1 AG. Okay, so this is the flow that I'm gonna be talking about, and I, of course, want to try to motivate why I'm doing this. These functions are the same that Julian was talking about in his talk, but this is an intrinsic conformal flow, so it's a quite different flow actually in behavior. When I started looking at this, I was expecting to see many more similarities, and actually there are some things that are quite different here. So with this in mind, let me try to give a motivation why you may want to look at something like this. Okay. So the first remark here is that when k is equal to 1, sigma 1 is some multiple times the scalar curvature, so you might want to define that up to a multiple, and that's okay, but I don't want to be carrying that number. So that's why I'm not going to put it there. So this flow here is actually the Yamabe flow. Let me give a number to, or like a sign to the equation that I'm going to keep up there. Let me call it star. And the Yamabe flow is quite well understood, at least in the compact case. So this is well understood. For M compact. And this was introduced by Hamilton in the 80s as an alternative idea to prove the Yamabe conjecture that at that time was already known to be true. So it was just like the idea that maybe a flow proof would be easier somehow than the non-flow proof, let's say. But yeah, okay, so for the compact case, this is very well understood. And in the non-compact case, the Yamabe problem is not true in general. So it's not known even today exactly in which cases you can find metrics with constant scalar curvature and when not, when you have a manifold that is not compact. So in that case, even that is, I mean, is somewhat, I mean, some things are understood, but there are many open questions even in that case. Okay, so let me say a few things about the non-compact case, because that would be kind of the focus today. So even for k equal 1, not completely understood, let's say. And in this case, there is a work by Bonjum here. Toti Daskalopoulos and John King, where they show that actually in the non-compact case, even for k equal 1, you can have singularities type 2 developing in finite time. So they prove that there are examples with type 2 singularities in finite time. And one of the things that they use in their work, I mean, maybe here I'm going to be corrected by the author, but one of the things that was important, I guess, to understand this is actually to know all the possible soliton solutions to this equation. So this uses the classification of solitons for k equal to 1. That it was worked by Toti again with Natasha Sesum. So, and in their work, what they do is they classify soliton solutions that are conformal to Rn and that are rotationally symmetric. So what I'm going to do today is generalize this result. So today, maybe just because Esther used so many colors, I want to use some as well. So today, we generalize this for other case. Okay, and okay. And I guess one question would be why you want to do this. I mean, that you can do it maybe is not enough of a motivation. So let me say one more thing about the sigma case. One motivation let me start with maybe this. So for n equal 4, the Gauss-Bonnet formula. And here, I'm sure again I'm gonna miss some of the constants, but you have something like this. You can write it in this way. W square plus sigma 2. Let me put the 4 here, and I'm missing some number there, I think, which is not very important here, but okay, let me leave it like that. This here is the Weil tensor. And this is the sigma 2 that I have here. Of course, this is a topological invariant. This is invariant under conformal changes, and let me put another integral there. So this is actually something that is invariant under conformal changes, this integral. So it's something that is related to topology, and somehow the idea again would be if you can find metrics where this is constant, maybe you can say something about the topology of the manifold. So you can connect somehow the geometry and the topology. In general, let me go up here. So in general, if M is locally conformally flat, what you can prove is that, and N is even, this integral is going to be a conformal invariant. So this is the measure in M. And what it turns out in this, and we're going to see it also in the results after that, that somehow this is kind of a special case that would correspond in some sense to the uniformization theorem in 2 dimensions. And when you have K, let me write it like this, K less than N, K to K equal to N, or to K bigger than N, you actually see very different behaviors in this case. That is something that doesn't happen in the extrinsic case. I mean, you see some differences, but here really these 3 cases are quite distinguished. And this is actually that shows up in the literature. Many people have studied this problem, especially in this case when N is equal to 4 and K is equal to 2. And in this case, it's pretty well understood the existence of metrics with constant sigma 2. But in general, I guess, unless you're locally conformally flat, not so much is known about this problem. And in the compact case, I think almost nothing is known. Okay, so that's kind of the motivation here to see how similar, how different is to the Yamabe problem in all these cases. I think I'm not very good with the chalk either. Okay. So was there something else that I wanted to see? Yeah. Here. Okay, so one disadvantage of trying to solve the sigma k Yamabe problem is that sigma k is quite nonlinear. This is a fully nonlinear equation. So in general, to solve, you will need extra hypotheses to have actually a PDE that is elliptic or parabolic if you want to do the flow. So we're going to need, in general, extra assumptions to have a parabolic PDE. And actually, in the fully nonlinear world of PDEs, I mean, these kind of equations have been studied before. They're usually called Hessian equations. And there's some standard assumptions that you would make in that case. Let me see if I can have another chalk. So in general, in this talk, I'm going to assume that we look for metrics in the positive cone. And that means the following. So we want metrics that satisfy that sigma I of G minus 1 AG is positive for I from 1 to K. So in this talk, I'm going to assume that in general, in the literature, you can find other things. You can also use the negative cone, for instance. And the negative cone is basically that minus G is in the positive cone. And the results here are quite different, so it's not the case. I'm going to try to explain why I'm going to use this one instead of this one, but you could also try to ask similar questions here. And otherwise, if you don't assume anything on where the metric is, you're really gonna run into trouble when you want to solve, because the equation is not gonna have enough structure, basically. Okay, so you need something. Okay, so maybe let me go back to the flow equation. So I don't know what time I started, but I'll try to not to make it a bit shorter, maybe. So previous work on the flow, as I said, there's not so much, but there's some work on the flow by Peng-Hei Wan again, and Wolf and Wang, I missed it. Wang, they study in the compact case, so M compact, locally conformally flat. They didn't have exactly the same flow. They changed a little bit the speed. They had the logarithm of sigma k instead. They explained to me something about the speed. And again, they studied the renormalized one that in the compact case makes sense. So here you have some, I don't know how to write it, but some kind of average of these to normalize the volume, basically. So it's a little bit different, but in many ways is similar. And in their case, they could prove under the locally conformally flat assumption and that 2K was not N, they could prove convergence to spheres, actually. So that's more or less all that is known for flows in this situation, I think. Okay, so what do I want to do? So today, we want soliton solutions. So I want G to be some function of T, some diffeomorphism phi on G0. This may depend on T. And if you impose this being a soliton, basically what you can find is that, okay, so in this case, the equation that you find is the following. You find that sigma k, or whatever is your speed here, actually you could pick a different speed, minus rho has to be the Lie derivative of G0, and I think there's a 1/2, and X is the vector field generated by this family of diffeomorphisms. Okay. So just to finish explaining the title of the talk, so this is the kind of solutions that we're gonna classify. Let me say a bit what is this rho and what is this x. I'm not gonna choose a random x, I'm gonna choose an x that is the gradient of a function, and that's the gradient part of the title. So if x is the gradient of someone, then the soliton is gradient. Usually phi, you call it the potential function. And this rho here is the derivative of tau at 0. And then actually you can rescale this equation and that's fine. So you only care about the sign of this thing. And when rho is positive, this is gonna be a shrinker. So I guess all of you more in flows, like for instance, this is gonna be something like square root of t minus t more or less. Not exactly, but almost. When rho is equal to 0, this corresponds to steady solitons. When rho is negative, this corresponds to expanders. Okay, so I'm gonna try to classify all these things under an additional assumption. And the additional assumption is something that we've seen this day. Well, one assumption is that I'm gonna be on the cone, but if Ricci is non-negative, then actually using splitting theorems, there's a result by Giovanni Catino, Carlo Mantegazza, and Lorenzo Massieri that just left. So if I make a mistake, no one is going to correct me on this, I guess. But in the non-negative case, basically you see you have three options here. It could be that your manifold splits. It could be, maybe I should actually change the board. So let me do it here. So if Ricci is positive, could be that M, you can write it as R cross N, and N has, again, Ricci non-negative. You could be compact, in which case the soliton is trivial in the following sense. The potential function is 0. So that means actually that sigma k is going to be constant. Or you're conformal to Rn. And rotationally symmetric. In their paper, there are many more things, but I mean, this is what I need today. Because what I'm gonna do, I think I have too many M's. It's rotational symmetric, so what I'm gonna try to talk today about is the classification of rotationally symmetric gradient solitons that are conformal to Rn. Okay, so now I guess that's all the motivation of what I'm gonna try to do today. I don't know, okay, I don't know if there are any questions before I continue. No? Yeah. There's one more work that sort of mimics their work in the negative case. And that's it, I think. And there are many people that has to try to say something about the trivial solitons also in these cases. And usually the result is that they're constant and you can, yeah. Okay, so let me tell you what the results are. Or let me try to at least say a word about what are the results. And then I'll say a word about the proofs. Okay. So the first theorem, and this is sort of based in the work for k equal 1. So the idea in general is that everything is going to translate into a PDE for the conformal factor. So we're going to basically first have to analyze what that PDE is. And for that, we're going to try to classify how are the rotationally symmetric solutions. Okay, so the first theorem is that if G, I remind you that I was writing it like this, and I'm conformal to Rn, so I'm going to write it like this, is a rotationally symmetric gradient soliton. Rotationally symmetric gradient soliton. Then, and this is a bit not super nice, but but you don't need to really understand. I mean, you don't really need to look at the PD. So there's just a few things that I want to point out from them. Over 2 du to minus 1 minus m over 2 square I. This is going to be equal, so it's not super nice. M plus 1 over 2. And here I'm going to have 2 theta plus rho u plus 4k theta m plus 2k x dot du. Okay, so I have not make things maybe much better, and actually I added like a few parameters here that I'm gonna be using all the time, so let me tell you what they are. And I kind of want to keep them there, but I guess the people at home won't see, so let me write it here and then I'll keep it there. That was my original plan, but I didn't realize they were not saying that. So M here.
You can keep it on the side. We keep it in our notes.
Okay, I'll write it for you to take notes, right? So
yeah, we have notes.
is n minus 2k n plus 2k, so it's something that depends on n and k. And theta is I'm gonna describe later what it is, but theta comes from the potential function. So this I'm gonna have to describe what it is, but actually it will turn out that it's a parameter that has some restrictions actually to be able to stay in the positive cone. Okay, so let me keep it on the side, just so I don't have to write it again. So the parameters that I have so far, k I'm not gonna write, but rho is the nature of the soliton. Let's say if it's a shrinker, a stereo expander. The soliton. M is gonna be n minus 2k, n plus 2k. And theta, for now, it depends on the potential function. I'm gonna say a bit more about this, and I'm gonna update the information there in a minute. Okay, so something that you see from here is that don't worry too much about what is inside here. The only thing that you may care about this equation is that you have a second derivative of u. So for instance, when k is equal to 1, you are gonna get a term here that is like a Laplacian. And if you want this to be positive, when you take this at x equal to 0, this term is not going to appear here. This is going to be a positive factor, because remember that for this to be a metric, I need you to be positive. So actually, being in the cone immediately implies that 2 theta plus rho has to be positive. Okay, so this is positive if G is in the positive cone. Okay, and this is going to be a restriction that is going to show up. So this is something that we want to keep in mind. For the results afterwards. Okay. Okay, so given that PD, as I said, what I want to do is classify what the solutions are. And the result is the following then. Let me see. Okay. Technically, I guess I have like 10, 15 minutes left or something like that, but I think I can say a little bit about this. So yeah, I mean, I don't want us to all finish at 7. I mean, everyone is going to remember me for not the correct reason, I think. So if n is bigger than 2k, then, okay, there exists a solution of the equation that I don't have anymore, but that I called star before, for every row with some prescribed value of 0. So it's a one parameter family. You can prescribe the value of 0 if and only if 2 theta plus rho is positive and theta is not negative. Okay? And observe the restriction here. As I said before, usually you have a distinction between n bigger than 2k and n equal to 2k. And the distinction, which I'm not going to write in detail, but the difference you see actually in how these solutions behave in the asymptotic behavior at infinity. I can give you details, but I guess I'm going to skip the solutions for, I think I lost this. Okay, for n strictly bigger than 2k, behave qualitatively at infinity as the case k equal 1. That is included here. But they're all the same, basically. They're all very similar to the Yamabe behavior. It doesn't matter which k, as long as you satisfy this. And the solutions for n equal to 2k, okay, I'm not going to be very precise, but they have different behavior, especially in the case of shrinkers. And that is the case that you really notice mostly the difference. And in this case, it's much more degenerate. And we cannot classify exactly how the solutions are here. I mean, we may have many different behaviors, and we're not sure. I'm going to try to explain why. So this is really kind of a limit case of this. In the case I still have existence, but the behavior is not very good. And I guess that's a spoiler for the next theorem. That is the other case. And in the case n less than 2k, we're going to see that solutions actually do not exist if rho is less than 2 theta. Let's say 2. If n is less than 2k, solutions do not exist for rho less than 2 theta, less or equal actually, if rho is bigger than 2 theta, and this is still positive, I still have that restriction, there are shrinkers that have, and I don't want to define this, but that has spherical behavior. Even in the case, let me just say a word about this. I'm not going to go into details because I want to say just like a couple of things about the proof. I'm not going to say too much. But even in the case k equal to 1, you see two families of solutions. You see what in their paper they call the Barenblatt solutions. There are solutions that behave, so this is the case for positive. Solutions at infinity behave like a to the minus, I'm going to make a mistake. I think it's 4, 1 minus m. Or, sorry. So you may have two different behaviors. And actually, this depends on the relation between rho and theta. And yeah, so one corresponds to what they are, even for the Yamabe problem, are called Barenblatt solutions, are the typical bubbles that you see in the Yamabe problem. And the other case corresponds to spheres. In this case, you only see spheres, basically. They're not spheres, but I mean, they have that kind of behavior. Spheres are solutions, but they are not the only solutions. And in the last, let me say, maybe 15 minutes, can I do 15? Yeah, but I mean, otherwise we're gonna finish like at 10, right? I mean, let me say a few words about the proof and where do you see the differences in everything and how you impose all these conditions. Okay, so some ideas about the proofs. About the proofs in general, I guess. Okay, so the first thing is that I'm gonna be interchanging a lot between R and this and S. So R equal to 0 is S to the minus infinity, and that's basically either parameterizing with spherical or cylindrical coordinates. And yeah, so I mean, when you see S, you have to think that that means that. And so the first observation, if you have a potential function, P is the potential, this implies that, okay, that phi s over, I'm gonna say in a minute what that is 0. And W here is R squared U to some power to 1 minus M. Okay, doesn't matter. So the point is that you have that this is constant, and this is how you deal with the potential function. This tells you what is the relation between the potential and the conformal factor. And what you can say then is that this is a constant, and that constant is what I call theta, 2 theta. That's the same theta that you have there. So when theta is equal to 0, that means that this is constant. And if you go back to the soliton equation, that means actually that the soliton is trivial. So theta equals 0 correspond to solitons with constant sigma k curvature. Okay, so this is the first thing. And that's the theta over there. So in some sense, we're really looking for theta positive because the 0 case is different somehow. Okay, so this is the first thing. The second observation if U is radially symmetric, we can compute the eigenvalues of the Schouten tensor. And again, it doesn't matter too much what they are, but I'm going to say it because it's going to show up in the restrictions there. Lambda 1 you can ignore. I mean, this is not going to be important today. I mean, it's important when you want to solve, but not for what I'm going to say. What is important about this is that this has multiplicity 1. And you have a second eigenvalue that you can write in this way. I'm going to write it a bit artificially, but you'll see in a minute why. And it's M over 4, I think, or you are, or you. And this has multiplicity n minus 1. So actually, you can see that being in the cone is going to mean that lambda 2 is positive and sigma k is positive. And with that, you can ensure that you're in the cone. This is equivalent to be in the cone. Okay, positive. Okay, so this is the condition. Okay. And because we have a very explicit form of this actually tells you bounds on the behavior of that. And what we're going to see is that lambda 2 positive lambda 2 positive means that RUR has to be something between 0 and some number that I just covered. So I think it's this. And again, you can compute now the equation in terms of the lambdas and solve. And what you're going to find out, which I'm not going to do, and I think you'll be willing to believe, is that sigma k bigger than 0, you can translate into a condition of that minus RUR over U is going to be less or equal than 2 theta plus rho. That is the other condition that I had there. 1 minus m times theta. And we're going to call this parameter gamma. And I'm going to keep the gamma there. Okay, so now you want to look at the equation in terms of these parameters and try to classify in terms of that. And I'm just gonna actually write the equation not very carefully, but and then I'm gonna make a picture, and I think I'm gonna try to finish with that. Yeah, I think we're gonna be okay. So the idea now is that we define x to be this quantity. And because it simplifies something, we're going to put a k there, but it doesn't matter too much. And this is going to be r squared u to the 1 minus m, I think, to the k, if I'm not mistaken, which I may be at this point. No, it's okay. And this satisfies okay, don't worry too much about the specifics. I mean, I'm going to point out in a minute what is the only thing that you need to look in this horrible expression. Some constant. K, 1 minus k. No, sorry, this is wrong. This is missing a 2 here, and what I was writing there, sorry, I was going too fast. And this is 2k. Say, what I was writing here was the f. So f is some constant, 1 minus k m plus 2k. It's 1 over k, 1 minus k. And here's the gamma. Okay, okay. Doesn't matter too much what these are. Okay, so the first thing that you should notice here, and the only thing that you may want to care about, is that the n minus k is showing up here. So basically what you're going to have is that this f is something that is positive, and somehow this term is going to have one sign when n is bigger than 2k, it's going to disappear when n is equal to 2k, and it's going to be positive when n is smaller than 2k. And that sort of quantifies sort of the change of behavior of these solutions and why some of them exist and some of them don't exist. Okay, so basically what you have to do now is try to find or try to understand how are the solutions for this system in terms of the parameters. And I'm just gonna make a picture to try to explain how you do this. Okay, so let me make a picture in the Yamabe case. Let's say when n is bigger than 2k. So the usual way, and this is what was done somewhere in the literature before the other paper, and is what the results are based on, you look for the critical points of that system. So let's say that this is x, and this is Z. So my restriction that I put here in blue is basically that my solution has to lie between, so let me mark two things. One thing is going to be n plus 2k over 2k. And then here I'm going to put n, let's see, n plus 2k over k, that is the other number. And there's the gamma, that is my other restriction that I don't know where I wrote, but somewhere that I wrote over there. And the gamma is something that is going to depend on rho. So gamma is something that is going to be placed somewhere here. So I basically, what I need is that my solution is before this blue point and before gamma, that gamma can move. Okay, so in all the cases, what I'm going to look at is what is the admissible region, and I'm going to try to find solutions there. With one more observation, that is when r is equal to 0 or s is minus infinity, x should be 0 if I want a regular solution, and z should be 0. Okay, so I want solutions that start here, that start at 0, 0, and that satisfy my two restrictions. In principle, this is what I'm looking for. Okay, so the critical points to the system here, if you look at constant solutions to the system, just as a system of equations. So the critical points in this case are 0, 0, n plus 2k over k. Actually, I think I'm missing a k somewhere. It doesn't matter too much. It's somewhere like that. And a point that is here. And some value that you can compute explicitly, but we don't care too much what it is. Okay, so when rho is negative, the gamma is going to be something that's somewhere here. Okay, so I want a solution that sort of lives here. And you can see from the equation from the f, and that's the only reason why I wrote what the f is. If x were ever to become gamma, then this first term would be negative. So that means actually you can never reach gamma. Gamma actually acts as an asymptote in this case. So in this case, you can show that you have a solution that starts from 0 and asymptotically approach gamma. And the asymptotic behavior is basically going to be given by understanding better the curve close to the asymptote. You can show that that exists. When, maybe I want a different color, or maybe I want a different picture, I don't know. When rho is 0, the picture you're going to have, I mean, you have the same critical points because that doesn't depend on rho. So you have a critical point here, a critical point that is somewhere here, and a critical point here. For 2k. You have the gamma exactly agrees with this. And again, you're going to have a solution like that. And in the case that rho is bigger than 0, same critical points, but your gamma has two options. It could be in between these two values, or it could be to the right of that. Okay? And these are the two different behaviors that you see. So, okay, gamma is somewhere here. And in this case, solutions start at 0 and reach this point B. In the other case, when gamma is somewhere here, solutions actually have a different behavior and start here and go to this point. And these are the two solutions that you see in that case. Okay? And just to finish, as I promised, in 15 minutes, when n is equal to 2k, you are going to see different critical points. You're not going to have this critical point here. In the case that rho is less or equal to 0, you're going to see exactly the same picture as you had here, but you're not going to have this critical point anymore. So all solutions are going to be like this red one, but they could go to anywhere on this line, actually. You could have anything like this when n is equal to k. And I should have chosen a different color. In the case that n is smaller than 2k, actually there's something I should have said before, but I mean, this case usually is much more rigid than the other cases. Actually, being in the positive cone is equivalent to having Ricci positive, and it's known to be more rigid. And what's going to happen in that case is actually you are not going to have solutions that are in the positive cone. You're going to have solutions, but these solutions are not going to be restricted by this gamma. They're going to start here and they're going to cross the gamma at some point always. So your solutions are never going to be admissible. You're going to have solutions, but they're not going to be admissible, except in this case of the red curves over here. And this is the only solution that you see in that case. And I think I managed in the 15 minutes, so I'm going to finish here.
Okay, thank you for your nice talk. Are there questions from the audience? Okay, there's one there.
Maybe a naive question. At the beginning of the flow, maybe you mentioned that, I forgot. So what is the asymptotic behavior of that flow?
Yeah, I didn't mention it. You mean in the cases that has been solved, or?
Yeah, like as
It's-
regularity.
Yeah, I mean, it's asymptotic to spheres. I mean, in that case, in that locally conformally flat case, it's regular, it exists for all times, and it converges to spheres, to something of constant sigma k, actually.
You mean the sigma k 1 over k with that speed?
With this speed, actually, there's no results for the asymptotic behavior, but for the logarithm one, you can do it in that case. And that's the only case that I think it has been actually done all the way.
Okay, thank you. Thank you.
Other questions? Okay, I have only one curiosity, in fact, that is whether this whole business, okay, for example, of the gradient solitons for Yamabe, could be meaningful also where you have a boundary.
Yeah.
And is there something known about this kind of?
No, I mean, this is a good question. In general, there are there's one result for what they call the singular Yamabe, right? I mean, that you have a boundary, but you converge at infinity at the boundary.
Already infinity.
Yeah.
Okay.
And
so,
this is kind of a non-compact, a controlled non-compact case, right?
Yeah.
But you can also impose like a curvature condition, yeah, right? For the Yamabe, you have a condition on H, basically.
Exactly.
Right?
This was my
Yeah,
question.
there are some things for that as well, but also not much is known. I mean, there's some proposals of what kind of curvatures you find, and you find the ones that Julian was kind of describing in the morning. You find this H case that he was.
I see. Okay, thank you. Okay, so if there are no other questions, it seems so. We thank the speaker again. Welcome back. We resume with the next and last speaker of this afternoon session, Rafe Matteo from Stanford. The talk is about families of minimal varieties with non-product cylindrical tangent cones.
Well, thank you very much. I hope everybody can hear me okay. Yep. Okay, I'll take a send as yes. Good, excellent. Well, first of all, let me just thank the organizers, Alessandra and Andrea, for inviting me. I'm extremely pleased to be included, and it just kills me not to be there. I wish I were there and learning all sorts of interesting things. So, again, I'm very sorry that I'm appearing here on Zoom. Anyway, I know it's late in the afternoon for you and very early in the morning for me still. So I've decided to try to be light on people and not give an ultra technical talk, which this talk could easily become. But I wanted to tell you about some work I've been doing, which is kind of a slightly strange thing from a geometric point of view, but it's kind of a basic question that one would hope you could knock off in a weekend. And it's taken me since the beginning of my career. I started working on this when I was a postdoc. Not that I've been thinking about it all the time, but it was one of those problems that was kind of bugged me that I wasn't able to do. And it turned out that it's actually a rather challenging problem. It's hard. And I've had a postdoc the past few years, Greg Parker, who I kind of realized that what he'd been doing in his thesis was exactly the tool that we needed to use to solve this problem. So I want to tell you about the general context and get you a little bit into what we've done and how we did it. But again, I'm not going to sort of give you all the gory details. So the general problem is one that you're all very familiar with, which is, well, let me state it in ridiculously broad generality. What do singularities of minimal surfaces look like? And I use minimal in a rather broad sense. So of minimal submanifolds look like. And I want to sort of be clear that I'm thinking this is going to be more of a PDE talk than a geometry talk in the sense that I'm going to be talking about minimal submanifolds really as thinking things as being hopefully fairly near to submanifolds and not thinking of integral currents or some other GMT type alternatives, which is often the right context to study variational problems. So I want to talk about embedded surfaces that may have some sort of complicated singular set. They're minimal in that their mean curvature vanishes away from the singularities. And in some sense, one of course, most interesting things, which are really minimizing or stable in a GMT sense, but are smooth in almost everywhere. So I'm going to be a little bit glib about what I mean by this. And so when I say what do singularities of minimal submanifolds look like, we all know that they can be very singular. And I'm thinking about, again, in great generality, things which are either codimension 1 or higher codimension, and again, of arbitrary dimension themselves. And there's a sort of a real spectrum of behavior. So, on the one hand, there's all the great regularity results, starting from Ongren and company, 50 years ago, 60 years ago. And so a large continuum of results to now sort of the very advanced and modern technology that's, progressed in an enormous way of sort of understanding, let's say, the size of singular sets, by which I mean that there's, very detailed theorems now about, if I have, for example, even in high codimension, how big the singular sets are in terms of Hausdorff dimension, sort of constraining them in ways, rectifiability theorems, and so on. So there's sort of a big gap between these. So on the one hand, you might imagine minimal submanifolds to be quite smooth. On the other hand, we know by many examples that they can have rather dramatic, complicated singularities. And one of the things I've been interested in is sort of, what's this sort of middle ground in between? By which I mean, if singularities do appear, the great dream would be that they would be kind of very well structured stratified singularities. We know that exists with algebraic or analytic subvarieties, for example, in Kähler manifolds. But on the other hand, the irregularity theorems are a long ways from there. We have, rectifiability is a long ways from having a stratified singular set. These counterexamples of Leon Simon from about 5 years ago show that, in fact, you can have these extremely messy singular sets, and many other people have found very interesting sort of generalizations and sort of side takes on that. But we know the singular sets can be sort of Cantor-like, just really arbitrary, horrible closed sets. What I'm kind of interested in ultimately is whether there's some sort of threshold behavior. So I'll come back to this theme later on, but I think that there's a real possibility that this, like many other nonlinear phenomena, have the possibility that singular sets can be really very bad. And then at some point, once you know that they're good enough, then they become extremely good. That there's sort of, let's say, for example, if you're in a smooth manifold, it's impossible to have a C5 alpha singular set, which isn't better, for example, just to be specific. So this is really the backdrop of what I'm talking about. Okay, so let me tell you about a very old story. And I'll give more details on this just because the setting of the way that this was set up was kind of important for what I was going to do. This was an old paper by Caffarelli, Hart, Simon that many of you may know. And this really was, as Leon Simon always told me this is what he famously used to call a junker. He said this is just a weekend project that kind of got out of hand. It led to all his great work on, uniqueness of tangent cones for isolated singularities, but the premise of what they were doing was really very simple. So you start off with a k-dimensional minimal submanifold in some sphere. You take a cone over it. So I let M be C1 of sigma, so the truncated cone. So it's well known that if sigma is minimal, this implies that M is minimal. It's mean curvature vanishes. And again, I'm thinking about this from a PD point of view rather than variationally. So I'm just thinking about mean curvature vanishing. And there are various embellishments like stability or minimizing, which one can add to this. And I'm not going to say very much about that just because I'm keeping my focus narrow for the talk. Okay, so the question they asked was the following. Can you sort of perturb this? I mean, just the very simplest deformation question that you can. And they were looking at a local deformation problem. So I'll sort of say this carefully. So a local deformation problem. Which is given a section of the normal bundle. So let's say it's a C. I'm going to be also very cavalier about regularity until it really matters, then I'll be more careful. So suppose I have a section of the normal bundle of sigma in the sphere. So this is n sigma in the sphere. Can we find a function u, which is a section of M, normal bundle of M, that's an Rn, such that the graph of u is minimal. Okay, so by the way I've set this up, and obviously I want phi small, measured in some norm, which I'm going to be very non-specific about, and then we're going to get that the norm of u is small. Ideally, something like this. So, of course, by setting this up as u being defined over all of M, what I'm really thinking about is a picture like this. So there's this exact cone. I'm going to perturb the boundary values a little bit in some way, and then solve the minimal surface equation. And their original goal, which was, an important one back at that, this was in the early 1980s, was can we find a big example of, a lot of examples of minimal surfaces, minimal submanifolds that have isolated conic singularities? And the answer is that if you can solve this, then you found many non-exact cones, which are minimal. So, so this produces many submanifolds, and again, it's local because they have a boundary at sort of the radius equals 1, so I always let r be this variable away from here. Many submanifolds, these are local in with isolated conic singularities. Okay, so that was the goal. It's a fairly modest one. They were able to answer this kind of completely. The answer is a little bit surprising if you've never thought about this before. I'll review what they did in sort of a modern take of the proof, which is really just the implicit function theorem if you set things up correctly, and then sort of say where it goes from there. So the answer is, let me just give you a brief answer. So brief answer. Yes, and you can prescribe phi not arbitrarily, but to lie in a finite codimensional space. So to lie in a finite codimensional space of boundary values. So in other words, if I look at the space of all functions, let's say, or normal sections on the boundary, there's some finite codimensional submanifold of ones which bound minimal varieties that have isolated conic singularities. Okay, so I'll get back to describing that, but oops, sorry for a second. I'll get back to describing the proof and how they did this. I just want to point out that this led to, so the consequences of this, so this was done in the very early days of this sort of approach to minimal submanifolds. So there were two famous consequences. One was this led to, all this great work of uniqueness of tangent cones at isolated singularities. Of course, that's true only with various hypotheses. but I'll just sort of say that as a general rubric. This is by, originally by Leon Simon, and of course it's been generalized to many other consequences, and so that's been an extraordinarily fruitful and important part of the subject. And the second thing is the genericity of, or maybe I should call it the fragility of singularities. By which I mean that, so here's the space of all boundary values, some sort of Banach space of all boundary values. Here's this finite codimensional submanifold. So these are, if phi lies in the submanifold, then this bounds a singular minimal surface. And the question is, what happens if I choose a boundary value somewhere off of that submanifold? We know we can solve the plateau problem, for example. What is that bound? And, this was studied very shortly afterwards. So if I have a minimal cone like this, and in fact, you needed stability or something a bit stronger than stability, then already Hart and Simon had showed that, again, in this local picture, if I take a one-sided perturbation, solve the plateau problem, I get something smooth. So this is kind of what's happening away from this finite codimensional submanifold, as you expect solutions to be smooth. They're not graphs over the entire minimal surface, of course, over the entire cone anymore. But this shows that, in some sense, if you move in a generic direction, the singularity is destroyed. So this, of course, has led to many great works. And I have to mention, because there was a beautiful paper posted just recently, but this is work of my colleague Otis Chodosh and Montelidis, Schulze. And I guess the most recent paper also includes Wang, and this is sort of the let's say, generic regularity up through dimension 11. And just to say very clearly what I mean here, suppose you perturb things. So in the Hart and Simon local picture, you were just perturbing the boundary values a little bit, and you could destroy the singular set. More advanced versions, or let's say more geometric versions are, suppose that you have an entire minimal submanifold, maybe compact and it has isolated singularities. Can you destroy those, or it has some sort of singular set? Can you destroy the singular set by perturbing the metric a little bit? So this has obvious a lot of geometric applications. It shows that if the singularities are not really there for topological reasons, then they're there only by some sort of accident of sort of choosing a bad metric, or some way to think about this. The original work on this was done by Nat Smale back in the mid-'80s. I don't know, maybe that was around 88 or so. And Smale and I did some later work on this about trying to destroy things, but somehow this has turned into a much more robust theory. That this work of Chodosh, Montelidis, and Schulze, for example, has really extended this in really extraordinary directions that I really hadn't thought possible back then. Okay, so that's kind of the setting with isolated conic singularities. And of course, this work I mentioned of Chodosh et al. Is not about isolated singularities here in higher dimensions. But the reason for talking about isolated singularities is we have such a good sense of what's happening near the singular set typically that it, you have so much control that, perturbing away becomes sort of a very manageable task, if you like. Okay, so there's a very natural question. As I say, it's kind of a silly one from a point of view, but can you do this with sort of non-isolated singularity sets? So what about non-isolated singularities? Non-isolated singularities. So let me give you the simplest example I can think of. Suppose I take this cone, C1 of sigma, and I cross it with just the real line. So I'm thinking of something that has a structure that looks like this. So again, I'm thinking of the local picture. So I let R be this sort of variable away from the singular set. So it's the radial variable on the cone. I have this sigma as the cross section of the cone, but then I have here I have the real line. This could be any sort of compact smooth manifold, for example. So I've just artificially created something that has a non-isolated singular set. So this is kind of a stupid contrived example, but you can ask exactly the same question that Kafferley, Hart, and Simon did. Can you perturb this so that the singular set becomes a little bit more complicated? You get things that are non-product type. Now, this may seem pretty simple and naive from a modern point of view, but back when this was being looked at in the 80s, this was, there were sort of very few examples. If you wanted to look for, let's say, hypersurfaces, minimizing hypersurfaces with non-isolated singularities, there were very few examples known that were not exactly products. I mean, there were things that were obtained with group actions and various other things, but there wasn't sort of an obvious mechanism for producing, let's say, minimizing hypersurfaces with these lines of singularities, or these sort of edges of singularities. So it's an honest question, can you sort of produce things by PDE methods rather than GMT methods? They have sort of more complicated singular sets. So you want to perturb to, I'll draw a bad picture, but something that, I've changed the boundary values a little bit. The singular set is now sort of wavering, and I have something which is no longer exactly a product, and the cross sections are no longer exactly cones. Okay, so you get the picture. I'm a terrible artist, but there you have it. So, you would like to set this up in the same way. So I'd like to sort of take a function phi, which is a section of the normal bundle. And this is, so now I'm going to have a manifold here. I'm going to call this whole manifold, let's see, what shall I call it? Z, let's say. And I have a boundary. So the boundary of Z is, in this case, it's going to be sigma cross R or sigma cross some other factor, sigma cross W. So I'm going to take a section, a section of the normal bundle of Z, and I'm going to find a U in some weighted space of functions. So find a U on the corresponding, so this is a section of the corresponding M normal bundle of M. So this whole ensemble is M, such that the mean curvature of U is equal to 0. This is shorthand for saying take the graph of U, compute its mean curvature, and so on. And crucially, I want U to be defined on all of M. And so this implies that the graph of U has as a singular set, which is in some sense some perturbation of the space W. So I had sort of the product space W before. So here's W, here's these cone over W. So this is W, and I want to perturb this to something where W is now warped into something more complicated. Okay, so everybody see the picture? Again, very simple, straightforward analog of what we wanted to do. So this is something, as I say, I started working on with Nat Smale when he and I were both postdocs together a very long time ago. And we ran into some problems, which I'll describe to you, and really got stuck. And I've thought about this problem over the years. And as I say, when Greg Parker came to Stanford, we started thinking about this. And I realized that, in fact, finally there were tools available to do this. So the answer at the end of the day is, and this is a theorem. Now it's work that we're just about finished writing up with Greg Parker, that this is possible. Namely, one can solve this PDE with sort of boundary values lying in some submanifold, which I'll try to describe for you. This is possible with various provisos. Maybe I'll say caveats. So let me state a very rough version of the theorem right now. So the first one is that phi is restricted to lie in an infinite codimensional submanifold. In the space of boundary values. So that's one proviso, that it's much less common to be able to solve this equation. You have to be much, much more restrictive in terms of where the boundary values lie. And then the second thing, which is even more surprising, is that the perturbation of the singular set is, I'll put extremely in quotes, extremely smooth. And when I say is, I mean must be. So this is sort of some form of elliptic regularity, or elliptic sort of regularity for an elliptic evolution equation, if you like. When I say extremely smooth, i.e., it's essentially got to be analytic. So in other words, I can't perturb the singular set in a way that just makes it a finite regularity submanifold. If this if here's W and I have these cones over it, this W, this image of W, this perturbed W here, has to be essentially an analytic submanifold. So that's kind of the surprise from one point of view. Now, in some sense, we shouldn't be very surprised because, the way I've always sort of thought of this question is it's sort of like a higher codimension free boundary problem. That, the way you might think about this is I'd like to sort of choose boundary values so that when I solve the problem, it's somehow everything is exactly focused so that the singular set kind of collects just along a submanifold. So, in some sense, you're saying you're trying to choose boundary values in a way that somehow the solution of the problem doesn't go seriously awry. I mean, it's not evolving in an ordinary evolutionary equation sense, but you can think about it as very ill-posed evolution as I move from the outer boundary into the inward boundary. And in order for things to evolve properly, you have to choose your boundary values really, really, really carefully. And when you get to sort of that final singularity, it's extremely smooth because it's evolved from something of finite regularity. So that's kind of very rough intuition, but I just want to say that I think that this is the right analogy. So this is analogous to some sort of free boundary regularity. Anyway, so finally, to return to this philosophical point I was making earlier, I think it substantiates what I was trying to say about there being a threshold behavior that, we just can't, you might well, and people can produce singularities, which are kind of very complicated and sort of not quite submanifolds or Cantor sets or sort of closed subsets of submanifolds. But the minute a singular set starts looking submanifold enough like in its own right, then in fact, there's some sort of organizing principle and it has to be very smooth. So that's really the moral of what my talk is about today. Okay, so let me now get into some of the details of the subject. And again, I don't want to sort of swamp you at this late hour of your day with too many technicalities, but let me give you sort of a sense of this. So let's return to the isolated singularity case first. So let's return to Caffarelli, Hart, Simon. And I'll give you a quick modern proof of what they did. Okay, so we have this cone with an isolated singularity. I have this function phi up here, and I want to find a section U which perturbs here. So U is going to be defined as a sort of a normal section here. Okay, so hopefully that picture is clear. Now, I'm trying to solve some sort of nonlinear PDE, H of U, where U is defined on the cone. So this H is, as usual, it's a quasi-linear elliptic equation, but the underlying geometry is conic, and when we know how to understand these things, we did already in the mid-1980s. But let me point out that its linearization L, the Jacobi operator, takes a well-known form. So this is going to be K over R. I think I've done my numerology right. 1 over R squared L sub sigma, where this is the Jacobi operator for sigma in the sphere. Okay, so it's what's called a conic operator, an elliptic conic operator. And there's a very strong and robust theory for how to deal with these things. And so let me tell you sort of the main points of the theory. So if I take this L, the natural thing to do is to let it act on weighted spaces. So I look at functions which decay like some factor of R, so R to the nu. And I'm going to use Holder spaces here. We can use Sobolev or Holder. It doesn't matter too much, but let me do this. I'm differentiating twice, so it sort of drops the weight by 2. And so this is a bounded mapping. And a theorem that's been known in some form or another since the 1960s due to Kondratiev and others, but has been improved in many ways since then, is that for nu not lying in some discrete set, which I'll tell you about in just a moment, and which I think many of you know about quite well, for nu not lying in some discrete set of values, this map is Fredholm. Okay. Now, this is a nice statement. Being Fredholm means, I'm almost in a range where it's surjective, so I should be in good shape. Let me sort of say this a little bit more objectively. So first of all, what are these? What is this discrete value? So we call, so the definition is that gamma is called an indicial root of L if there exists a function psi on the cross section. So let's say my cross section is, let's say, call these things sigma. such that L of r to the gamma psi of sigma. Well, what would ordinarily happen to a function like this? I differentiate it twice. I'm going to have some function r to the gamma minus 2 times some new function of sigma. And being an additional root means that this vanishes. It's big O of r to the gamma minus 1. So there's some sort of leading order cancellation. So this turns out to be a generalized eigenfunction type of eigenvalue type of equation. And in fact, it becomes the following equation. So it becomes, so if I just plug this in and use this form of the operator, so up this form of the operator up here, what I'll get is that gamma times gamma minus 1 plus k times gamma plus L sub sigma of psi is equal to 0. Okay, so it becomes like an eigenvalue equation. So it says L sub sigma plus gamma times gamma plus gamma plus k minus 1 of psi equals 0. Okay, well, don't hold me to my arithmetic. I might have gotten off by k going to k minus 1 or something like this. One can solve the values. So if I let L sub sigma of psi is equal to minus psi j is equal to minus lambda j of psi j, so just the spectral data decomposition for the Jacobi operator for sigma, then I'm going to find that the gamma j's come in pairs, gamma j plus or minus, and if again, let me plow ahead with my numerology I have in my notes rather than what I have on the screen. So I'm going to get the following things, k squared plus lambda j. So these turn out to be the sort of the values of, so remember, this means that r to the, one of these values, r to the gamma j plus or minus psi j, is going to be, in fact, on the exact cone that's exactly equal to 0. So these are kind of these special product form singularities. Okay, so what it shows is that, if I were to take these types of functions, so let's suppose I have r to the gamma j plus times psi j, that would be a very particular function, and I can find a solution of the homogeneous linear equation, which vanishes like some high power of r. Okay, so that's kind of the import of these equations. Now, let me draw the weight axis. So remember, I was letting L acting from r to the new c2 alpha b to r to the new minus 2 c0 alpha b. So here is 0. Here is this number minus k over 2, which is sort of the center point of this calculation here. And then these initial roots are distributed in symmetric pairs around here. And where are the significant weights here? So 0 is obviously always a significant weight. That just means that I have perturbations which are bounded as r goes to 0. But there's another very important weight, 1, because if I look at perturbations which vanish like r to the new, where new is greater than 1, that means that the graph of u has C1 of sigma, has C of sigma as its tangent cone. Okay, so in other words, if I take a perturbation which vanishes faster than linearly, then the tangent cone hasn't changed. Okay, so in some sense, we'd really like to work with weights nu which are bigger than 1. Okay, so somehow that's a magic threshold for the geometry problem. On the other hand, and this is again sort of very old knowledge, that so this operator L from, I'll write this one last time, c to alpha b to c, or the new minus 2 c0 alpha b. This is Fredholm, but it's surjective only when nu is less than gamma 0 plus, which is always way less than 1. Okay, typically this gamma 0 plus is negative. So on this weight scale, maybe here's gamma 0 plus. It's the first guy to the right of minus k over 2. And any weight over here, in this range here, whenever nu is in this range here, I get a surjective problem. And if I go up further, I'm going to start developing co-kernel. So that's kind of the trouble. There's a tension between the analytic requirement of looking for a surjective operator and the geometric requirement of wanting things to vanish rather quickly. So that's kind of the fundamental problem here. So if we can find a space, let's call it for the moment, x sub nu, such that L from script x sub nu to r to the new minus 2 c0 alpha b is surjective, and nu is greater than 1, then we can apply the inverse function theorem, gives the result. Okay, so it's just a trivial application of the inverse function theorem, provided we can find a function space in which this operator is surjective. Okay, so here's going to be the space. So I divide up. So I'm going to define, so I have this, well, let me just say L2 of sigma, and I can divide it up into eigenspaces plus E sub j. These are the eigenspaces for L sigma. So if I have a psi j is live in EJ, then I have the eigenvalue L of sigma psi j is equal to minus lambda j of psi j. And it turns out that I can divide up these things into two ranges. So I can look at this set where j is less than or equal to j, and j is strictly greater than some capital J. What is this capital J? Well, what I want is that this number, gamma j plus, is going to be greater than 1 if j is greater than capital J. So remember back in this weight scale, here's this threshold 1. That was the geometric cutoff. I have these initial roots which appear on various sides, and I choose the very first one to the right, and that determines sort of which eigenspaces I include. Okay. Okay, so the answer is finally the following. So this space X nu is going to be the following. So it's going to be the space of functions u in R to the nu C to alpha b, such that if I take u at R equals 1, this is my putative phi, and I project it onto this these guys. So the projection here is I'm going to call pi j perp, and here's the projection is going to be pi j. So if I project onto the eigenspaces with j is bigger than j, so in some sense all of these initial roots, this is equal to 0. Okay, so in other words, I'm imposing Dirichlet conditions, but only on the eigenspaces where j is sufficiently large. Okay, so then we get surjectivity. So then L mapping x to the nu to R to the nu minus 2 Caesar alpha b is surjective. Okay, so why is that? Okay, well, there's a duality argument. So Caffarelli, Hart, and Simon had done this by separation of variables, but I want to talk about it by sort of more abstract principles. So this is just a duality argument. So the dual operator, L star, is identified with L acting on sort of a negative weight. So what I'm going to do is I'm going to write nu is equal to minus k over 2 plus some mu. Its dual weight, let's call it nu check, is going to be minus k over 2 minus mu. So in other words, in this sort of funny scale, I have this set up here. Here's my nu, and then there's going to be this dual weight down here, nu check. Okay, and R to the nu check minus 2 Caesar alpha b. So here's the dual problem. I'm looking at this thing on this dual space, whatever it is. So it's the adjoint domain. So this x to the nu check is going to be the space of u's in R to the nu check C to alpha b. I'm being, again, glib about regularity because the regularity interior doesn't matter too much for these isolated singularities. But so that pi j perp of u at R equals 1 is equal to 0. And if I take pi j of u at R equals 1 and its normal derivative, pi j of u du dr, dr of u at R equals 1, these both vanish. Okay, so this is just a statement that if I'm at a boundary and I am imposing no restrictions at R equals 1 for these low eigenmodes, then the dual problem has every restriction. The full Cauchy data is vanishing. Okay, so this is just duality. So that this operator, because it's sort of morally symmetric, its dual is just going to be itself on a different weighted space. But the boundary conditions are the same for the high eigenmodes. And for the low eigenmodes, I'm imposing this incredibly restrictive boundary condition at R equals 1, where I demand the whole Cauchy data vanish. So the point is that this is obviously injective. And that does the trick, right? So I'm done. So I get sort of easy injectivity here. I had this Fredholm problem, and I wanted to know if it was surjective. I just look at the dual problem. If it's injective, then it is, and I'm happy. And then we solve the nonlinear problem by the inverse function theorem. Okay, so I went through this in more detail than I would because when we look at the non-isolated singularity case, I'd like to replicate exactly the same story. Okay, so when we have the situation of M being C1 of sigma across, and now I'm just going to stick in the very simplest case where I take C1 of sigma across a circle. Okay, so this is going to be the issue. So I try to apply the same argument. Everything seems to go through with a couple of provisos. So for every eigenspace, so if I look at this space W, which is going to look like sigma cross S1, I have the eigenspaces here. So I have L2 of sigma divided up into a sum of eigenspaces. Each of these eigenspaces is finite dimensional. But if I look at L2 of sigma cross S1, this is going to be divided up into a sum of eigenspaces tensored with L2 of S1. So every finite dimensional eigenspace of the problem just on the cone becomes infinite dimensional because I have all possible functions in the S1 direction. Okay. So what does that mean? It means that obviously, if I'm making these restrictions, so I'm constraining things to I'm not prescribing the boundary values for the first J components, I've actually lost an infinite amount of information. So I've lost all of the ability to prescribe boundary values in J less than or equal to capital J if I apply the same argument. Okay, so immediately we see, so we take the sum J less than or equal to capital J of this EJ's tensor L2 of S1. This is infinite dimensional. But, this dual problem, this L acting on this corresponding space with vanishing Cauchy data at R equals 1, this is still injective, so it seems like I can just do the same darn thing, right? I'd have a surjective problem. So the difficulty, and this is really the core of the analytic nightmare, the difficulty is that the original L, mapping R to the new C2 alpha E to R to the new minus 2 C0 alpha B, does not have, and let's say with no restrictions on the boundary values, in these low EJs in the pi J component. So this is sort of what we did in the isolated singularity case. So I just restrict to these sort of low eigenmodes in the sigma direction and let everything else be normal in the other components. In the isolated singularity case, I had a nice Fredholm problem. I sort of relaxed these finite number of conditions, and I was able to get a surjective problem. Here, the problem is no longer Fredholm. And in fact, even worse, it's not that it's even semi-Fredholm. In fact, it doesn't have closed range. Oops. So let me just give you a brief sense of why that's true. Okay, so again, here's where the technicalities really start. But suppose I look at the Jacobi operator in this non-isolated singularity case. So I'm going to write out what it looks like, k over r dr plus 1 over r squared L sub sigma. And now I'm going to have this extra piece, d theta squared. So this is sort of the new feature. It just comes from the edge. Okay, if I look for solutions of L of u equals 0, I'm now going to find perfectly nice solutions. And here's what they're going to look like. So u is going to look like, and let me just sort of write it this way, r to the minus k over 2. And then there's going to be an I sub mu j of r mod L times psi j of sigma, or r to the minus k over 2 k sub mu j of r mod L psi j of sigma. So these are Bessel functions of an imaginary argument. The L's are the, so here I have the J's index the eigendata of sigma. And the L's correspond to really breaking down into an eigenseries in the S1 direction, e to the I L theta. So I've just done a double separation of variables. And again, this is for illustration purposes, and this is not really necessarily how one would like to do the analysis, but this is what we're doing for illustration. And so the point is that solutions of LU equals 0 break down into these products of eigenfunctions on sigma, these functions on R with these Bessel functions of imaginary order. And here's the sort of kicker, that these I sub mu's of R mod L, as R or L get big, these things are looking like e to the R mod L, and the k sub mu's of R mod L are looking like e to the minus R mod L. So all of a sudden we've introduced this sort of exponential type behavior. Okay, so this is from a technical point of view. This looks like, well, kind of weird functions, but c'est la vie. But let me show you how that plays out. Let me take a much simpler operator just to give you a sense of what goes wrong now. So let's look at the really dumb operator that everybody knows all too well. Suppose I'm just looking at this problem. So this corresponds to like dr squared plus d theta squared. And I've separated variables in the circle in the theta direction. So this is really for illustration. This is, if you're of a certain turn of mind, as Semyon is in the audience somewhere, right? This is a nice semi-classical problem. So what do the solutions look like? The only point I wish to make is that suppose I have a function f which looks like r to the nu minus 2, where nu is sort of anything possible. Suppose I look like f looks like u to r to the nu minus 2. What does u look like? So, and let me make clear. Suppose that f looks like 1 times r to the nu minus 2. You solve this equation, and what I'm going to get is going to be something that looks like e to the r mod l divided by mod l squared times e to the times r to the nu. So you can solve it exactly, and of course it's not exactly that. It's going to involve hyperbolic signs and so on. But if I want a solution which decays, so here's the kicker, is that I'm thinking of nu as being bigger than 1. I want a solution which decays like r to the nu. So that's kind of putting this restrictive thing. I'm trying to solve up from r equals 0. So I'm trying to impose as much decay as it could possibly have as r equals 0. And in order to do that, it's growing exponentially. Okay. For any fixed r is equal to 1/2, for example, it says have exponential blow up in L. Okay, so the moral of this is simply that unless, and so I should have said this is like, let's say UL and F sub L. So unless the F sub L's are decaying like e to the minus r mod L, I'm going to be in trouble. So this is really the moral problem in the whole thing, that we have to work with function spaces where we have this exponential decay in the decay or the eigen of these corresponding eigencomponents. So that's really where we're at. So the upshot is that we need to work in these terrible function spaces. Upshot, we need to work in function spaces with exponential decay of the corresponding eigenmodes, of the corresponding coefficients, at least as L goes to infinity. Okay, so that's plain and simple, and I've given it in as simple a version as I can. Okay, so what do we have to do? Well, the point is you have to define function spaces and you have to do a whole bunch of stuff. So let me just at least tell you now what the problems are that we have to face and what do we have to do about it. So ultimately, what we do is the following. We have to define appropriate function spaces, which introduce these exponential weights. With exponentially decaying coefficients. Okay, well, fair enough. That doesn't seem so bad. Here's the kind of where the trouble starts. Even so, there's a loss of regularity. So in other words, if I have function spaces, which let me call them x to the nu again, but now I'm going to sort of put in another variable, let's call it tau. So these things have, let's say UJLs, eigenmodes, which look like e to the minus r mod L, and then I'm going to put in a mod L to the tau. Okay, so I just demand, I look at function spaces where the eigenmodes have forced exponential decay, right? And, or maybe I want a 1 minus RL, but this is basically the type of decay one needs. And then you have to include this polynomial decay. Then loss of regularity means the L will sort of decay from order tau to order tau minus 2, but the inverse does not gain you a full amount of 2 orders of tau back. So the problem is that then you have to work in a Fréchet scale. So you need to work in a Fréchet scale. Namely, Namely, I have to look at these things over all tau. So I might sort of fix And then this is going to be times an r to the nu. So I still enforce this r to the nu decay, but in the eigenmodes, I get this sort of very, very quick decay. Okay, so we have to work in a Fauché scale, which means that ultimately we have to use the Nash-Moser implicit function theorem. Okay, so to cut a very long story short, that's what we do. But let me just point out 3 problems and basically what are the things that have to be overcome here. And that's really the moral of what I want to say today. So the first thing is we need to show that these function spaces behave well. Behave well under all the compositions. All the nonlinear compositions, etc. So to be very clear, this problem occurs precisely when J is one of the small eigenvalues on the length sigma. And when J is big enough, then I don't have to worry about this sort of exponential damping. So the point is that can we define function spaces which just require exponential damping in the low eigencomponents and not the high components? The answer is no, because of course the nonlinearity is going to mix everything up. So, you have to deal with function spaces which have this exponential damping in all variables. Okay, so that's sort of problem number 1. And, so this means, if I have a function that satisfies this and I take a polynomial in it or I take a smooth function of it, well, what happens? And so that involves looking at the mean curvature operator and seeing what are the specific types of operations that you do to these functions and to say that that's preserved. So it turns out that the best way to handle this is that we use Grout tubes. And so for those of you who don't know this is a very beautiful trick, or a method or a, beautiful theory coming out of complex geometry, which is that suppose I have let me call this W, which is a real analytic manifold. Then if I look in its cotangent bundle, there's a small tubular neighborhood around it. So suppose I take a small tubular neighborhood in the cotangent bundle. So this is in T star of W. This small tubular neighborhood can be complexified. So I'm really taking the complexified cotangent bundle. And so I'm looking sort of in the imaginary direction. So I sort of think of this as being an imaginary part, and this is the real part. So I'm thinking of W as being a totally real submanifold, and then the normal directions are going to be the imaginary directions. And it turns out that when the radius of this thing is small, this is actually a strictly pseudoconvex neighborhood of W. And then here's the very beautiful thing. Any real analytic function defined on W extends to a holomorphic function on the Grout tube. And a way to measure regularity so if I have a real analytic function, U, which is real analytic on W, a norm for the real analyticity is I take the U, which is the holomorphic extension, and I'm just taking, let's say, the sup of U, right? So the supremum of this holomorphic extension, this gives us sort of the real analytic norms on little u. Okay, so it's the radius of the tube. So it's sort of how far out it extends holomorphically, if you like, the radius of the power series that tells you how real analytic the original function is. So the nice thing is that then I can take, the nonlinear functionals that we're talking about, the polynomials or derivatives and so on that are required for the mean curvature operator, and just see how they extend on these holomorphic extensions. And then we just have to bound sup norms rather than bounding sort of more complicated, taking the Fourier series and sort of bounding exponentially the thing. So this Grout tubes formulation gives a very neat way of understanding this problem, but that's kind of one big technical foray. The second thing is that we need to prove tame estimates for the inverse of the linearization, tame estimates for the So by tame estimate, I mean that, well, if L is mapping, let's say I have these spaces x nu tau to, r to the nu minus 2. Well, let me just say, not being too specific, x nu minus 2, tau minus 2. Then, oops, I need to, sorry, there we go. Then I need to take an inverse G, And, this needs to prove x to the new minus 2, tau minus 2. It has to go up to some x to the new tau, and then there's going to be some sort of small loss there. But this delta is independent of tau. So I don't recover the full regularity, but at least the drop in regularity is uniform over the entire Fréchet scale. And I not only have to do that for the inverse, but I have to show that all of these sort of nonlinear operations also satisfy so-called tame estimates. So this is kind of a usual mess with the Nash-Moser theorem. And then the third thing is I need to do all of this not just at the product C1 of sigma cross, C1 of sigma cross W, but at all nearby surfaces. So what do I mean by all nearby surfaces? Well, I have the exact cone. I look at all possible perturbations. So I have all possible sort of slight wigglings of this thing where the singular set has gotten sort of a bit crazy. I no longer have a product structure, and I still have to, make sense of all of this. And all of the analysis I told you before, I was kind of implicitly doing this sort of separation of variables. So the point is you really have to move away as much as possible from a separation of variables type formalism to really proving these estimates in a much more robust way. And this turns out to involve, so let me just say briefly, this involves a new gauge. Namely, we first took perturbations, we perturbed them just by, so it's sort of a gauge choice by saying I just look at normal graphs. I'm looking at graphs, it's sort of turning it into a PDE is kind of a particular choice of coordinates or a gauge. But once I've done that, so I've realized this thing is a graph, so realize is a graph. And then I have to do one more strange thing. I have to uniformize in the variables r and theta. And by uniformizing, I mean exactly in the complex analytic sense. Namely, I have these two variables. Here's sort of the circle. Here's the radial variable of the cone. Here's theta. This has gotten perturbed to some sort of wiggly thing in general. So here's the product case. Here's sort of the graph case where this thing is wiggled. I have to now choose the uniformizing map by the Riemann mapping that maps this to a circle of still exactly length 2 pi. So this is theta. This goes from 0 to 2 pi. And this now goes from 0 not to 1, but to some, let's say, function, let's say t of just some other variable t. So why do I have to do something like that? And I just wanted to say that in a word, and then I'll be just about done. So why do I have to do something so complicated? So this seems like just a kind of a minor thing, but I just want to mention some deeply philosophical mistake that we made if we don't do this, right? So remember, we were looking at functions that decay like e to the minus r mod L, or e to the r minus 1 mod L, or things like this. Okay, so we had exponential dampings of functions that had various types of decay rates like this. Okay, so this L here is predicated on a circle of length 2 pi, right? So those are the eigenvalues for a circle of length 2 pi. If I perturb this whole picture, so if I have this circle, I have this whole minimal cone here, and I perturb this whole picture so that, the singular set becomes something more complicated, then this perturbed circle, this S1, let's say perturbed, let's call it, phi of S1 or whatever we're calling it, this no longer has length 2 pi, which means I'm using the wrong function spaces. So I have the wrong exponential dampings if I've done this perturbation. Okay, so somehow what this reuniformization of talking about does here is it says, let's move everything back to a case where I have circles of length 2 pi uniformly. That's kind of a global thing. I have to reuniform. I have to solve a PDE to get this new gauge. And then I've destroyed the upper boundary value. So I've said that this upper boundary value no longer occurs at r equals 1. It's, there's a one-dimensional conformal modulus. And so we lose one extra bit of control over what's happening to the boundary values, maybe is the best way to put that. So those are kind of the three subtleties that we have to face here. And, as I say, I'm being light on details here just because to really explain this carefully is kind of a real morass. But I just want to say that the real The real technical innovation here is what came out of Parker's thesis. So real technical innovation is one that if you're in the nonlinear hyperbolic world is kind of old hat. And in some sense, in the nonlinear elliptic world, it's kind of a much less familiar tool. So this comes from so it comes from Parker's thesis, which is engaged theory. So it's a very different looking subject, Parker's thesis, my collaborator, Greg Parker. And the technical innovation is we want to use mode-dependent cutoffs. So again, not a shocking tool from many other parts of mathematics, but at least in this kind of context, it was kind of an unusual thing to do. And just to be sort of very clear, when I encounter a function that looks like e to the, let's say e to the r mod L, right? This function, when r is positive and L is getting arbitrarily large, as we have to consider, this function becomes uncontrolled. We'd like to cut off in the region where r is less than or equal to 1 over mod L. So in other words, that's what I mean by mode dependent. I've taken the Fourier modes in the circle, and then the cutoff regions for various constructions in the geometric radial variable have to depend on what Fourier coefficient I have. So really, it's some sort of micro-local cutoff, which is, again, kind of very standard in other parts of analysis, other parts of PDE, but in this kind of minimal surface setting, I've never seen anything used quite like it. Greg used it to very good effect in his analysis of a study of multi-valued spinors in gauge theory, and I kind of recognized that this was going to be exactly the right technical tool to sort of employ in this problem. Okay, so I think I've flogged you enough for this late in the day, but this is kind of the problem. So, again, the result is, maybe ho-hum from some point of view, but technically it was one of these things that was kind of driving me crazy for, let's say, an embarrassing number of decades, because it turns out to be really quite a subtle one. So I'm answering just a very naive geometric question of, can we sort of perturb minimal wedges? It's a very modest geometric goal. Analytically, it turns out to be quite a heavy lift. And this is just, of course, a local problem. If we want to understand the whole problem globally and, far away from the product situation, different singular sets in the circle, it's going to be probably requiring more robust tools, but at least it's kind of a proof of concept that this kind of thing can be done. So the upshot is that we've now produced a huge number of examples of local examples. So they're just defined for r less than or equal to 1, but I can construct a lot of non-isolated, smooth singular sets with cylindrical tangent cones and non-product type as advertised. Okay, so I'll stop there.
Hi, this is Xuan.
Oh, hi.
You mentioned that the solution will be behaving very well, like almost analytic. So
Yeah.
where does this analyticity come from?
It comes from the fact that the Fourier coefficients are decaying exponentially.
Oh, it's because of your exponential, that's exponential space. That's why everything is just covered there. Okay.
That's exactly right. So if you take something, if you take any function, you expand it in just the circle, and the Fourier coefficients are decaying exponentially, then the corresponding solution is when I re-sum them, then I get something real analytic. So that's really the reason.
Thank you.
Okay, another question there.
Hello, Rafe. This is Lan. Thank
Hi.
you for a beautiful talk. So I have 2 questions. I think the first question is about when you compare it to the Cavalli Hart-Simon result, in the case you are handling like a larger set singularity, and the Jacobi operator is no longer Fredholm. So do you have a geometric explanation of why this could happen? And the second question is about your new gauge. So I wonder if the new gauge is related to something like you are not looking at normal graph only, but you take into account the tangential part. So you are looking at graph over, like a different, not necessarily over the normal vector, or is something more complicated? It's not just like you taking into account the diffeomorphism on your like a model space.
Sure, yeah. So let me answer the second of those questions first. So yes, I mean, it's really, we're doing something global. We're sort of taking a graph and then we're kind of doing, composing it with a solution of some PDE, this reuniformizing thing. And, I think of it as very analogous to I mean, the old beautiful theorem of Müller and Sverok, for example, about, if you have the mean curvature, just reparameterizing the sphere using a conformal thing to say that, if you have something with curvature which is very close to one, then there's sort of a good conformal parameterization. So there's a number of antecedents of things like this where also morally, like in gauge theories, like Uhlenbeck's theorem, that if the curvature is well controlled, then up to gauge, there's a connection with which is very well controlled, which has that curvature. So you have to do some auxiliary, elliptic re-gauge fixing in order to sort of get the optimal solution. There's many possible ways of parametrizing this one, and you're using sort of a precomposition with a solution to some PDE to get sort of the one with optimal regularity. So that's kind of the answer to that. For your first question about, this non-Fredholmness. So this is really kind of this philosophical, let me just sort of say a few words. Let me just sort of add another screen here. So, there's a very old theory that you all know for conic operators or cylindrical operators. And as I say, this goes back to the Russians in the 60s, Kondratiev and so on, but this is, the work of Lockhart and McCohen, this sort of Fredholm theory in conic spaces, the work that Melrose did, and, many, many ways to do this. I mean, conic problems are analytically very simple in some sense. I mean, they're singular, but they're really pretty easy, and everybody and their mother can do it. So you have a Fredholm problem, and it's not very difficult from a sort of a modern perspective. When you have these edges, then it turns out that, so again, if I look at sort of this weight scale, so, I have these sort of bad indicial roots where the range is not closed. And if I look at the operator L as a mapping from some R to the new C2 alpha to R to the new minus 2 C0 alpha, then what happens here is that as nu increases, I'm imposing a higher and higher weight at the vertex of the cone, and things get, more restrictive. And so, I'm losing null space because I'm sort of putting more restrictions, but I am gaining surjectivity. So, I mean, the right way to say that is that the index is getting more and more negative, and things become injective eventually. And if nu goes in the other direction, then I'm gaining surjectivity, but the null space gets bigger and bigger. So this is very much like what happens in Rn. If I take weighted solutions of the Laplace equation, which are, very heavily weighted positively at infinity, then I have no solutions, but there's a huge co-kernel. And if I allow sort of a negative weighted infinity, then I have all the harmonic polynomials up to some degree, but it's surjective. Okay, so this is sort of an old story. So for these edge problems, I could draw a similar sort of weighted axis. But it turns out that every time I cross one of these initial roots, I lose an infinite dimensional amount. So the point is that there may be some small, narrow range of weights here where I have a problem which is Fredholm or, an isomorphism. But typically, when I sort of let the weights be more and more negative, I pick up infinite dimensional null spaces, or in this direction, I pick up infinite dimensional co-kernels. So that's one thing that's already bad, but that's still semi-Fredholm problems are still pretty simple from an analytic point of view. The thing that really goes bad here is what I kind of illustrated with that simple example, this e to the minus r, which is that, if I want to sort of pose a boundary value, so if I want to solve L of u equals f, and I want f to decay, so I want f to look like r to the new minus 2, where nu is big, right? And I want a solution which is like r to the nu, and nu is big. So what I'm doing is I'm kind of integrating up. Okay, now on a cone, if I'm sort of integrating up from the vertex, that's a fairly simple thing. You can write down on each eigencomponent with sort of variation of parameters. I mean, that's just sort of solving an ODE, and you can find a solution which decays as fast as the right-hand side. When you're trying to do this here, you run into these sort of, you obtain these sort of exponentially growing solutions. So that's really the kind of the much worse problem that we're facing, is that the range becomes non-closed, and it's because I'm demanding something that from an analytic point of view is extremely unnatural. I'm demanding that my solution decay very rapidly as r goes to 0, and the analysis is screaming that that should be impossible. It's like trying to solve an ill-posed Cauchy problem or something like that. So the analysis is trying to tell you this should not, under any circumstances, be possible, and you can only do it on this sort of very thin, dense subspace of analytic things. So that's really kind of the reason.
I see.
If that
That's
makes
great
sense.
answers. So here you are looking at like a different boundary conditions, right, to make it better.
Yeah, so that's exactly right. Yeah.
Right. Yeah, thank you.
Sure.
Okay. Other questions?
May I ask one?
Okay, Andrea, online.
Hi, Rafe.
Hey.
Yeah, great talk. I was wondering whether possibly for some proper boundary data, that curve of signal points could break into segments, say?
Of course, I mean, yes, it can, and I think Leon showed us that that's exactly what can happen. But how you engineer that, I mean, that's kind of, this whole setup is kind of engineer defining graphs which are, which maintain the singularities, by virtue of, trying to solve a PDE on the wedge, that's sort of demanding that my solution not sort of break up the singular set. Of course, it's extremely interesting about how you might break up the singular set and can you do it in segments? And then, I mean, Leon's construction was, in some sense rather similar. He was looking at these sort of normal graphs, but then he was sort of messing with the metric in sort of this complicated way near the singular set to try to sort of smooth out the singularities and sort of arbitrary bits. So that's kind of a very different sort of setup. So I think that just by the nature of how we set things up here, the answer is no, it's not amenable to doing that. But of course, there are other ways of setting up to arrive at other goals. And, that's been done and successful in other cases.
Great, thanks.
Okay, other questions? Okay, it does not seem the case. So we thank once again Rafe